the section that we'll be dealing with today is called kinematics. Now this is going to be in one dimension. All right, so this 1D basically means this one is for dimension. Okay, this is just 1D, so in one dimension. Now what are kinematics? Basically, when you're talking about kinematics, you're looking at you are tracking motion with respect to time in whatever form. So you could track it along a line, so a straight line. So in this case, we'll be just looking at a straight line, along a straight line. So this is what kinematics in 1D is. Kinematics basically is just motion. So you're just tracking, you're studying motion in a way. That's what kinematics is. So it is possible to have kinematics in 2D. It is possible to have it in 1D. So just to briefly explain the difference between 1D and 2D. If I have something like in a straight line, like I have a car that starts here, and then after some time it ends somewhere here. So I think all of us can just agree that this car actually just traveled in an x direction. So we can find the displacement, we can find the time and the change in time or whatever we're looking for over that period. Okay, so it's just in 1D. Another one is someone is at the rooftop and then they decide to drop a ball straight down and then the ball hits the ground. Okay, so if you look at this, the ball just traveled in the direction of delta y. So you can find the distance from here to here, and that is delta y. So this is one dimension because it's just one direction. Basically, it's either in the x or it's either in the y. Now, what about 2D? Now, 2D is a bit tricky, and we are not going to deal with 2D in this section. So 2D, how 2D works is you have a ball. Let me say you shoot a ball in that direction. So the velocity is in that direction. So after some time, the ball will be here. So we are assuming that there is no friction. So there's no air friction. So that's what we are assuming. If we assume no friction, no air friction, so after some time, the ball is going to end somewhere there. Okay. Now let's look at what is happening here. So what is happening here is your ball has traveled the distance that it has traveled. We can't say it's x or y. Let's just call it delta x s. All right. Now you would say that if someone was here, when they look at the ball along this direction, the ball has traveled some distance x, and the ball has also traveled some distance y as well. So you can see that it actually traveled 2 dimensions and then it will be at an angle. All right. So if you were to draw the displacement vector, the displacement vector will be like this. And then this was going to be equals to the x direction. So this is you are resolving the vector into components. And then this is going to be the y direction. So this would be like motion in 2 dimensions. So you could find the speed also in that direction. You could find the acceleration and everything else. It's a little bit complex, and when you're dealing with 2D, and it's a bit challenging as well. So normally this is done at varsity. At high school, you'll just be looking at motion along a straight line. So for our case, we're just going to look at motion in 1D. Okay, so it's fine even if you didn't understand what I just explained. Don't worry, don't stress yourself too much about it. Okay, so now what about this motion in 1D? Okay, so the first thing to talk about in motion in 1D is to just talk about the quantities that we'll be looking at. Okay, so the first quantity that we'll be looking at is a quantity that we call the distance. Now the question is, what is the distance? The distance is the actual path that was taken. I remember in high school we used to define it like this as well, so I've crammed it from then, and it's true, it's very true. Now for instance, let me say for instance I'm moving from my home and I run in this direction and then I turn and then I go this way, and then I turn, and then I go that way, and then I turn. I'm running in the street, right? And then maybe, and then I stop somewhere here. All right. So the blue line is the actual path that I took to get to this point. If I call this point A and I call this point B, the blue line is the actual path that I took. I went down and then I curved here. Then maybe you find that this actual path, when I calculate the kilometers I covered, was 12 kilometers. So that is the distance, right? And for the distance, we are going to use the letter D to actually signify the distance. Now, the displacement, however, is different. The displacement in this case would be, I started at A, I ended at position B. So the displacement is, it doesn't care. You just draw a straight line from where you started to where you ended. And that is going to be the displacement. So for the displacement, I'm going to use delta S. Now, you will notice that I'm putting this hash thing here, this arrow thing here. Now, what that means is that the displacement is a vector. It has direction and it has the magnitude. Now, what I would encourage is that you go and watch my videos on vectors so that you understand what is magnitude, what is direction. So delta S is actually the distance displacement. Maybe you find that delta S is smaller, the magnitude of delta S. Again, if you watch my videos on vectors, you'll understand why I'm writing it like this. That's why I started with vectors. Maybe you'll find that if I was just to fly, if I could fly, right? If there was nothing, maybe there are houses here. That's why I couldn't just go from point A to point B. But if I could fly, I would just move from this point to that point. But I can't fly. Maybe I'm driving with a car or I'm running. So I would have to go out and follow the road to just get to that place. Maybe this is a mall. But if I could fly, I would just move straight from point A to point B. But since I can't fly, I have to use the road, and then I have to actually take a longer path, which is 12 kilometers, and that is your displacement. Now the displacement is just going to be a vector, which is from the starting point to the ending point. It's just a straight line. So the difference being the distance is what we call a scalar. Again, go and watch my videos. Scalar just has size. So distance, we just need to know how big is it. That's why we say the distance is this big. But the displacement is a vector, right? So what it means is that I can't just say the displacement, I can't just say it's 2 kilometers. I'll have to say 2 kilometers in what direction, all right? Maybe let me say if I put a Cartesian plane here, and maybe the angle here was like maybe like 12 degrees, then I would have to say my displacement delta S is equals to 12 kilometers. Sorry, not 12, 2 in this case. It's going to be 2 kilometers, right? And my distance is going to be 12 degrees, and then maybe 12 degrees. I'm trying to just maybe let's just say 12 degrees from the positive x-axis. All right, so you're just saying it's 12 degrees from the positive x-axis. There it is. And then you're just moving 12 degrees from that positive x-axis. There are many ways you can do this. I mean, you could go and say you went to the east and then the north, so you could say 12 degrees north of east. You could say that as well. All right, or you could say 12 degrees above the horizontal, the positive x-axis. You could say that as well. Instead of using from, you could say above. So most of the books would say that they would say like 12 degrees above, and I think this one is more appropriate, above the positive. They would say that maybe when they are giving you a problem state, positive, there should be I, the positive x axis. Okay, right. So just go to the videos where I was just dealing with vectors, and then I taught all of this. So that is why now I'm just speaking as if you already know what I mean by that and that and that. So don't do this section until you have done vectors. All right. Okay, so that is the difference between distance, and that is the the difference between displacement and distance. Okay, so that is good, I think. So I haven't really calculated much yet, right? We're still gonna calculate a lot. All right. Now the important thing is when you're dealing with kinematics, there's someone who's sort of telling the story, and so we need to sort of find out who is this person, or even if we don't know who, but how do they know what they know, and that person is actually called the observer. So we are going to discuss how the observer knows all of these things. All right, so that would be the observer. All right, okay. Okay, so we're just going to be looking at that. So what is the observer? All right, so we want to find out what is this observer that we're talking about. And so an example would be, you would be given a problem, for instance, when you're writing a test, and they would say a car is moving at a constant speed of 2 meters per second over a distance of maybe 3 kilometers in 3 minutes. Now, here's the question: who is telling me about this car? So, someone should have measured that there is a car that is moving at 2 kilometers and it is going to cover a distance of 2 kilometers in 3 minutes. So, how do we know the time? Who is talking about this car? Who's seeing this car? And then they are measuring, who's measuring how far they are, when, and so forth. So the question is always phrased in the perspective of the observer. So there's someone who is an observer. So for instance, I would give you an example. When you're reading this question, this situation is already described to you as a car that is already moving, but we know from reality, I mean, the taxi can't just somehow magically have 75 kilometers per hour. So we know in reality, maybe it was at the taxi rank, and then when it was at the taxi rank, the speed initially was 0, right? It was 0 kilometers per hour. Then the taxi driver got into the taxi, started the car, then the taxi maybe started moving. As it was moving, it was from 0, maybe here it was something like 2 kilometers, 3 kilometers, 10 kilometers, 60 kilometers, 80. Maybe they slowed down to 60 and then 70. Then maybe when they reached this point, they were already moving at 75 kilometers, and then they continued moving. Maybe at some point, then they started to slow down. Maybe at this point they slowed down, and then at this point they reached 60 kilometers per second, and then they continue to move with that speed. So here it was 0. Maybe here it was like 80 kilometers per hour, but here it was 75 kilometers per hour. So the observer who is telling us about the situation was not at the taxi rank. They were not there when the taxi was doing all of this. They started seeing the taxi here. So that's the observer. So maybe this is someone who is at a university or wherever they are. They started seeing a taxi when the taxi was somewhere here. So the observer was here, the taxi was here. So the observer and the taxi were in the same position, right? Another way you could say, well, the taxi is here, maybe the observer is just standing here. So the taxi is directly across the observer. All right, so the observer is seeing a taxi, and maybe let's say the observer has something, a device that measures the speed, and when they are seeing the taxi, they look at their device is telling them that this taxi is moving at 75 kilometers per second. Now after some time, this observer notices that, oh, the taxi is now slowing down. Now the observer is still here. The observer is not moving with the taxi. The observer should always be someone who is standing still, describing something that is moving. So they look at the taxi. When the taxi is here, the taxi starts slowing down. Then when the taxi is here, they realize that when the taxi is there, they measure their speed, the speed of the taxi. Oh, now the taxi is moving at 60 kilometers per hour. So this whole question, and then the observer realizes that from when I saw the taxi to when the taxi reached 60 kilometers per hour, it took 3 minutes to do that. So how does the observer know this? So we're going to talk about the time and everything else. So the most important thing is there is an observer who is describing motion. In actual fact, almost all problems that you will get in physics, they are always described from a perspective of an observer, whether someone is doing an experiment. For instance, I'm an experimental physicist, so I will go and do an experiment. Then I will measure something, maybe on whatever it is that I'm measuring. Then I'm reporting that, okay, we did this, and then we saw this atom, and then we measured this. Well, you can't see atoms, but then we actually detected this atom, or we detected this interaction, and this was the parameters. So I'm describing the motion from my perspective of as a person who was doing the experiment. And so this is very important. So that is who the observer is. So whenever you get a question, don't assume that no, everything must start from zero, because that's where students make a mistake. The question is always going to be interpreted from the position of the observer. The observer was not at the taxi rank. So the observer did not see the taxi starting at zero, turning corners, reaching 80, decreasing, and then to 75. The observer only started seeing or describing motion when the taxi reached 75 and the taxi was in the position of the observer. All right. So this is the most important thing that you should also understand about the observer. All right. So somehow, unless it is like a good way to assume that the object was at rest, there are instances where you can assume that it started at rest. Maybe we'll look at questions, and then based on how the question is, we can always assume that if they don't tell us that it started at rest, it may be good to assume that it started at rest. But this is not always the case, right? So you must read the question very carefully, and you must always understand that there is an observer who is describing what is happening here. The observer saw a taxi. Maybe the observer, was their home. Maybe this is their home. They saw the taxi. When they saw the taxi was already moving at 75 kilometers per hour. And then 3 minutes later, they saw the taxi is now moving at 60 kilometers per hour. So they are telling you that, hey, I saw a taxi here. It passed me at 75. And then after 3 minutes, it was moving at 60 kilometers, and then it just continued moving. So it's more like your friend is telling you what happened, the situation that happened. So your friend is an observer. Or you are telling your friend, so you are the observer, say, hey, yeah, I saw a taxi passing me at this point, and then it moved. It was moving at 75 kilometers, and then it continued to move. After 3 minutes, I saw it was passing by so and so's house, but then when it passes that house, it was already at 60 kilometers. So you are the observer, and it's very important that you understand the position of the observer. Okay, so now we are going to talk about the position from the perspective of the observer. We are going to talk about time from the perspective of the observer, because this is very important. So I've already told you what is displacement. I've already told you what is distance. I've already told you about the observer. Now I'm going to sort of try now and put everything together so that you understand, and start telling you guys about how do we then describe, how does everything gets described from the position of the observer. Okay. All right. So that's what we're going to do now. All right. So let me say, for instance, I have an observer. There's my observer. All right. So this observer not actually takes notice of a car. So we're gonna use, right? They are here. When they look at the car, they see the car is already somewhere here. So the car is already, let's say, 3 meters away from the observer. So when they started describing motion, the car was 3 meters away, moving to the right. Okay, and then after some time, the car was somewhere here. All right. Then when the observer was now trying to measure how far is the car now, the observer realized the car is now 9 meters away from where I am. So everything is described from the position of the observer. So I first saw the car. The car, when I saw it, I am at position 0. So the observer is always at position 0. All right. So always when you talk about what is x, what is the position of the observer, the position of the observer is always 0 meters. Okay. So if they don't tell you, so a question like this would be, a car is 3 meters away and is traveling to the right. Okay, full stop. After maybe 5 seconds, the car is 9 meters away. All right, after 5 seconds. Now let us look at this thing. The observer is the green dot, so the observer is at 0. So when they first described the motion, maybe when the observer got to this position, the car was already 3 meters away from them. We don't know anything about the speed of the car, so I just want to talk about the position of the car, and I also want to talk about the displacement of the car, and I'm also going to teach you how then do we interpret the time. All right, because that's also what confuses students. All right, so the car was already 3 meters away, all right, when I first saw it. And then the car, after 5 seconds, it actually covered, it was now at 9 meters. Now maybe a question would say, what is the distance, not the distance, let me say the displacement covered by the car over 5 seconds. All right, now let's look at it. So the observer was here at position 0, but the car was already at position 3 meters. After 5 seconds, the car is at 9 meters. So the car took 5 seconds to move from 3 meters, that means the red color, to move from 3 meters to 9 meters. That's in 5 seconds the car moved from position 3 meters to position 9 meters. So now I'm introducing something. So when you observer saw the car, the position of the car and the position, we are going to call it, the initial position is x0. The second position is going to be x1. All right, that's the second position. Okay, now the initial position of the car, according to you, it was already 3 meters away from you, and after 5 seconds it was 9 meters away from you. So that is the position of the car with respect to where you are. So we are measuring everything. How far is the car from the observer? When I first noticed it, it was 3 meters away. How far is the car from the observer after 5 seconds? Then the car was 9 meters away. Now the question is, okay, from when I first noticed the car to when the car reached the position of 9 meters, how much distance did the car travel between those 2 points? So if this is point A and this is point B, what was the displacement that was covered by the car? Now the displacement is always going to be measured as the final position minus the initial position. And when you are actually measuring this, you must put the signs. Okay, I'll do a problem now whereby it becomes negative, and then you can actually see why it's important that you must include the signs. All right, so you are talking about a vector here, so it's a vector minus a vector, so that is why it's important that you put signs. Then the next thing is you must always choose what is going to be the positive direction. So of course it's going to be somewhere here, so I'm always going to choose the x as positive, and then I'm going to choose everything going up as positive. So which means that anything going to the left, I'm going to take it as negative. Anything going to the right, I'm going to take it as positive. Or anything to the right of my position is going to be positive. Anything to the left of my position is going to be negative. That is when I'm looking at the distance. All right. So hopefully you guys are following me and you are not getting lost. All right. So we want the displacement from position A to position B. What is position A? Position A is when I first saw the car was 3 meters away from me. After 5 seconds, the car was now 9 meters away from me. Okay, so position B is the final position, and position A is the initial position. So if I want the displacement for that part is going to be, the final position is going to be 9, the initial position is going to be 3. So what you do is you just take whatever values that you have here. So what is x0? So in this case, you will say the displacement is going to be x1 minus x0. So which means that I am going to say, okay, fine, x1 is 9, and then because x1 is 9 meters away from me, that's why I say it's 9. And then whereas x0, which is the initial position, is 3 meters away from me, so that is why I'm putting 3. And then you'll find that in actual fact the car covered 6 meters during the 5 seconds. So the car basically covered the distance, the displacement of 6 meters, right, in the positive x direction. Remember I said that in the positive x direction, or you could say positive x axis, or you could say to the right. You could also say to the right as the direction. Remember, since it is a vector, it must have the size. How big is it? It is 6 meters. What is the direction? It is going to the right. Again, go and check out my videos in vectors, and then you'll understand everything that I'm doing here. Okay. All right. So this is very important that you guys understand this, because if you get lost here, this is where it becomes very difficult for you to deal with kinematics. All right. Okay. So how about the time? So we know and we understand what's happening when it comes to the displacement. And the distance that is covered by the car from here is the same. I mean, the distance in this case is just going to be how much did I cover from here to here. So the distance is going to be 6 meters as well. So it's going to be the same as the displacement. So all along we are going to track the distance, we are going to track the displacement so that we understand what's happening. Now the question is, what about time? Okay, what about time? Okay, so remember, when the observer saw the car was already 3 meters away, all right, according to the statement, and it was traveling to the right, so the car was traveling in that direction. Okay, and then reached this point. We don't know what's happening with the velocity, whether it stopped, when it got here, it continued, we don't know. And that's another thing. What you don't know, you don't know. Don't assume you know something that you don't know. You don't know anything about the speed, you don't know anything about the velocity. So don't even talk about it, because it's not, nothing is said about it here. All right, of course you can calculate it, but nothing is said here. For instance, they didn't even tell you that it's traveling at a constant speed or not. You know, so even when you calculate the speed or velocity, you need to be careful. What are you calculating? But we're going to talk about that as we proceed. Okay, so let me just redraw the whole situation and then now discuss it in terms of time. All right. Now, what is happening in terms of time, the whole situation? There's the observer is here. All right. What is happening with the car? They first see the car is 3 meters away. After some time, the car is this meters away. All right, so x0 is 3 meters away because when we started, the car was already 3 meters away. X1 is 9 meters away. Okay, and then we found that, okay, fine, it's going to cover a distance of a displacement, or a distance in this case of 6 meters away to the right, of course. All right, so I'll just throw an arrow that shows that it's going to the right. All right, so you'll notice whenever I write a displacement, I would say equals to, and then you put the size here. How big is that? You put the size, so it is 6 meters big. Then you say comma, and then you put the direction. Put the direction here, and then you say comma, and then you say to the right, and that is the direction. So they are going 6 meters, they cover 6 meters going towards the right from your position. Remember, everything is defined from where you stand, right? And so from your position, you saw them going to your right. So it's important where you are, for instance. So if they were going to your right, right? So moving away from, you could also say away from the observer, it's fine, right? And then provided that you told us where the observer is. So you'd say that the observer is at this position, so they are moving away from the observer. So you need to be very careful and know exactly what you are talking about whenever you talk about this. Right now, how about the time? All right. So you are told that it took them 5 minutes, 5 seconds to move from 3 to 9. Now the question is, what is this 5 seconds? All right, so when you as observer saw the taxi, you had a stopwatch with you. So you always assume that the observer has a stopwatch. So in the minute they see the taxi, their stopwatch is reading 0 seconds. That's when they start counting. Okay, they start counting, and then they find out that when their stopwatch is actually saying t is equals to 5, this is t1, sorry. When they look at their stopwatch is saying 5 seconds, and then they look at the car. How far is the car? The car is 9 meters away. So this time here, like this is the position, and then these are the actual times. Let's put it like that. Actual time. So this is the time it is that you are reading on your stopwatch. So this is your stopwatch reading. Stopwatch, so PCH reading. This is what you are reading. This is what you see on your stopwatch. All right. But then when the question is written, normally they will not give you the time on the stopwatch. When they are writing this, for instance, you must look at it. It says that a car is 3 meters away and is traveling to the right. After 5 seconds, the car is 9 meters away. All right. Okay. In this case, they are telling you the stopwatch. All right. This is after 5 seconds, meaning that when I looked at my stopwatch was 5 seconds. So after 5 seconds, that's when I saw that the car is 5 minutes. Is actually 9 meters away. Now, this after 5 seconds, it mustn't confuse you. It doesn't mean the time after 5 seconds. When they say after 5 seconds, just think of it like your time watch is 5 seconds. And then that's where you actually record it, because there's always the uncertainty time between looking at your stopwatch and looking at the car. So, but then we are going to ignore that uncertainty, that error, because it takes some time to move your eyes away from the stopwatch to the car, right? So in a way, we're going to say after 5 seconds, because in a way, when you say after 5 seconds, just think of it like we are taking into account the error, but the error is very small. We assume that there is no difference in time between you looking at your stopwatch and you looking at the car. All right, that's what we are assuming. All right. Now, if it's written like this, they are actually telling you what is happening. What is happening with your what is happening with your car. Now, it is very different. For instance, if they said is moving to the right in 5 seconds, the car covers a distance of, right? So it will be different. And then let me say, for instance, they said to you, if they wrote the same question and then they say, let's use a different color. And then if they say to you, a car is 3 meters away and is traveling to the right. Okay. And then in 5 seconds the car covers a displacement or distance of 6 meters. Now we are going to interpret the two. All right, so the first question they gave you the actual times that are on the stopwatch. How I know this is because they are telling me how far is the car after a certain time on my stopwatch. So they are telling me after how many it covers that, Now it could be tricky. We're just gonna do different examples and then try so that you are able to interpret exactly what is happening, because that's where the struggle is. All right, so if you were to just take the change in time, right, let's just continue with that problem. If you are to take the change in time, all right, if you are to check the change in time for this situation, which is the green question, you would just say change in time is going to be the final time minus the initial time. Now in this case, what is the final time? T1. What is the initial time? T0. Now your time should always be positive. Once you get a negative time, you did something wrong. So what is the final time? The stopwatch is 5. What is the initial time? Is 0. So you can see here that it took 5 seconds to actually get to 9 meters. So the question is right. Now let us interpret the same question, but now for this black. Like for instance, if we're given this statement, how would we actually interpret the position and how would we interpret the time? All right. So now we are interpreting it when we are given this question. I actually came up with this question when I wanted to explain how they give you time and how you should interpret time. But along the way, I just thought it might actually be a good idea to separate the two situations. All right. I prefer teaching live. So when I'm teaching this, I'm actually making the things, I'm actually coming up with questions so that at least you understand, because I'm trying to assume I'm teaching you live. I don't want to have everything that is planned and then I'm teaching you. So I'm assuming you are in class and then I'm teaching you, you have questions and I'm trying to answer your question. So I have a car that is 3 meters away. Okay. I have a car. So this is how you read the question. A car is 3 meters away. You stop. You go and then you draw the observer and then you draw a car that is 3 meters away. That's how you interpret the question. So this is the observer. This is where the observer is. Then where is the car? The car is 3 meters away. That's how you draw it. Okay? Then you continue reading. When you continue reading and say and, so in your mind you'll put a comma here. And it's traveling to the right. Oh, so the car is traveling to the right. So the car is traveling that way. If they said the car is traveling to the left, and then you say the car is traveling that way. So don't just throw everything when you are done reading the question. Another way is you can read the question, finish it, then come back and actually interpret it. That you could say the car is traveling 3 meters away and is traveling to the right. In 5 seconds, the car covers a displacement of 6 meters. All right. Okay. So I will have a car that is traveling to the right, and then it's okay to 5 seconds. It will take it 5 seconds to cover a distance of 6 meters. Okay. All right, so and then you come back and then now you interpret the question. All right, so when you are reading the full question, you don't draw anything. And then you're just giving yourself a picture of what you really understand. You have a clue of what is happening. Then that's when you go back, now you are really analyzing the question. Then you first read the first part and say a car is 3 meters away. So when you feel you have enough information, stop there, go and draw that information. All right. When you feel like, okay, I have enough information already. I have some information. So it doesn't have to be enough. And then you just have some information. And then it says, and it's traveling to the right. Oh, also it is traveling to the right. So this car is traveling to the right. So the velocity or the speed of it is going to be to the right. When the speed is a magnitude, the velocity is going to be right because the velocity is the vector. Then you continue. And then they say, in 5 seconds, the car covers a displacement of 6 meters. All right. So there should be covers here. I know my writing is bad, guys. I'm left-handed. That's my excuse. I always say that. So I can't write very displacement of 6 meters. All right. So, okay. So I have a car. So in 5 seconds, the car covers a displacement of 6 meters. Or another way they could say this, they could say the car covers a displacement of 6 meters over 5 seconds. So they could also say it like that. It would be the same thing. So this is how you draw it now, so that you don't assume, okay, so the car was 3 meters away, and then in 5 seconds, it covered a displacement of 6 meters. So I have a displacement of 6 meters. Now, I don't know the position. So you mustn't assume you know. You can calculate it, yes. How long did it take to move from this point and cover 6 meters? It took 5 seconds. And this is what I wanted to actually talk about, the change in time. To say, when you are given a question like this, they are giving you the change in time. This is not the time in the stopwatch. This is the time that when someone has a stopwatch and then they work it out, they say, oh, it actually took this long to get from that point to that point. This is something like this. You say to someone, they ask you, okay, when did you leave your house? And then you say, I left my house at 10 past 11. And then they say, when did you arrive at the mall? I arrived at half past 11. Then they say, oh, so it took you 20 minutes to get to the mall. So how did I get the 20 minutes? They said 11:30 minus 11:10, which gives you 30 minus 10, and then you get 20, which is 20 minutes. That's how they know. So they are only telling you how long it took you, but in their head, they actually worked it out. Okay? So in their head, they actually worked it out. So you don't know the actual position yet. You could calculate it, but you're not told. So whenever you are not told something, put a question mark. Don't assume you are told, because normally the question is going to ask you to calculate anything that has a question mark, right? If, for instance, I was testing you on this, I would say find the final distance after 5 seconds. Now the final distance is going to be from the observer to where they ended up. It's not from point A. If this is point A to point B, it is not from point A to point B. The final distance would be from point A to point B, or the final position will be from this, not point A, sorry. The final position will always be from point O, which is the observer, to point B, not from point A to point B. All right. So since you have a question mark here, they are probably gonna say, what is the distance at position B? So you can find that. You can say, well, I know delta x, which is 6 and it's positive because going to the right. And then I know that the final is going to be x1. Moving from A to B is going to be x1. And then this is going to be x0. So I'm going to use what I know to find what I don't know. All right. So you can't use a displacement from O to B because you don't know this distance here. So you can't do that. Try and use A and B because you know something about A and B, so it will help you find the position at B. All right. So you know that the displacement is going to be 6. And then the final position, I don't know. This one is going to be 0. Okay. And then so from that one, sorry, this one is going to be 3, not 0. Why am I saying 0? I was pausing because I felt something is wrong here. And then this is going to be 3. All right, so you can see here, you will take this and then you'll put it this side, and then you'll end up with 6 plus 3 is going to be x1. All right, and then which means that x1 is going to be 9 meters. So do you see how I can get that x1 is going to be 9 meters? And this is why it's important that your x, you see, for instance, if you said x0 is 0 meters, because a lot of people always assume, no, whenever you start a position, put 0 meters there. That's not true. What I can tell you is the time you must always put 0. The time is always 0. Right? Whenever you start describing motion, the stopwatch is 0. And then here, t1 is going to be 5. How do I know that? Because it took 5 seconds to move from point A to point B. Therefore, if I do delta t is equals to t1 minus t0. What is delta t? It's 5. What is t1? I don't know. What is this? This is 0. And then you do the mathematics, and then you find that t1 is going to be 5 seconds. That's how I know that t1 is going to be 5 seconds. All right? Maybe to just explain it again, because so that we all understand. If, for instance, you were asked to find out because how long did it take you to get to t1? Let's say you don't know. Then you want to calculate it. You'll say, well, I know how long it took to move from point A to point B, and that time I'll call it delta t. So delta t is the time I took to move from point A to point B. And then how do I get that time? The final time at point B is going to be t1. I'm going to call it t1. The time at point A is I'm going to call it t0. So which means the time from point A to point B is 5 seconds. There's 5 seconds. Then this is all is going to be equals to the final time at point B. I don't know, so it's t1. And then what is the time here? And then this is 0. So you take 0. 0 is nothing, so which means that t1 is going to be 5 seconds. Now it means that the stopwatch, when they go to point B, then the stopwatch was actually reading 5 seconds. So this is very important. You need to know the time that you calculate in your head. This is the time you calculate in your head. This is the stopwatch time, right? So at those positions, those are stopwatch times. This one, you are calculating it in your head. Calculate in your head or using equation. So you can calculate it using an equation in your head. You can use a calculator, whatever, right? You could use a calculator as well. So this is what you calculated. And sometimes normally the questions, they give you this time or they ask you to calculate this time. Now these ones are generally what is reading on the stopwatch. So I'm going to extend this question now and make it longer, and then so that we have the positive cases and the negative cases, and then we can actually understand from this what do we mean when we say something is actually going to be positive and negative. All right, so I'm taking time teaching this because it's very important that you understand this, because if you don't understand this, it's going to be a nightmare to solve everything that we're going to work through. All right, okay, so let me extend this question. I am going to extend this question and I'm going to make it longer. All right. Okay. So let's see how we can actually do that. So I'm trying to think how to extend it. Let me say I have an observer here, and then they see a car, and the car is initially 3 meters away when they see it, and then after some time it is 9 meters away, and then it continues moving, and then after some time it is what, 20, let's just say 20 meters away from the observer. So x0 is 3 meters away, and then x1 is going to be 9 meters away, and then I am told that it then travels a displacement. All right, it travels a displacement after, so from point A to point B to point C. I am just given that the displacement from this point to this point is going to be 11 meters. All right, and then I am told that it took 5 seconds, sorry, to get to point B. All right, and I'm told that it actually it arrived at point C after, so I am given that it arrived at point C after 15 seconds. All right, so this is the information I'm given. So what do I know? What is that I don't know? Okay, I know that the car was initially 3 meters away, and then it took 5 seconds to get to 9 meters. Okay, and then it covered a further 11 meters to reach another point. But then at that point, the time, not x, the time when it reached that point was 15 seconds. Now let's see. So I'll need x1, and then when it's here, I'll have to call it x2. So which means that I'll also have t0 when it's here. What is my time on my stopwatch? Is 0 seconds. When it's here, what is my time? I am not given. I have to calculate it. When it's here, what is my time? I'm told that the time when it's there is 15 seconds. All right. And then here, I don't know the position. I have to calculate it. All right. And what is it that I also don't know? I also don't know the displacement from A to B. I'll call it displacement 1. I also don't know the displacement from B to C. Maybe let me just use that displacement from B to C, A to B. I don't know those displacements. So I don't know. Oh, I know that one. That is A to B. I know it. What I don't know in the second interval is the time. I don't know the time, right? I don't know changing time from B to C. That's what I don't know, right? This one I also don't know. What did I tell you? There are questions I'm probably going to ask you. Find the displacement between A and B. Find the time taken to move from point B to C. What is the position when the car reaches its final destination point at point C? That is what the question is going to say, and it will probably say to you, find the time when the car is at point B. So wherever there's a question mark, that's what the question is going to ask you. So that is why it's very important to do this thing, and this is called a model. You are modeling your problem. It's very important that you do this because it's going to provide you so much clarity when you do this. All right. So now let's say, for instance, I want to find, I'm not going to write because I'm lazy to write. Now, from here on, I'm not going to write problem statements. I'm not going to, this is just me trying to teach you how to check what is what. And then when we probably do tutorials and stuff like that, and then I'm going to actually go through how you interpret questions. All right. Okay, so that I don't actually hide this. So maybe number one, they would say to you, find the displacement between A and B. So in order for you to find delta x AB, you just say the final position at B is going to be x1. All right, the initial position at A is going to be x0. If you want, you could put xb here, you could put xa here, you could put xc here, but you shouldn't be confused by how we are actually numbering things, because what happens is if you start cramming things like that, when you change one thing, you get confused. You reach a test and now there's no XA, there's no XB, and now things are just, they are called X1, X2, and then now you get confused. So I don't want you to get confused. So that is why I'm using different notations. All right. So if you wanted that displacement, what is the final displacement is 9. What is the initial is 3. Therefore, delta xab is going to be 6 meters to the right. Okay, so I'm just going to use positive x direction like this, and then which means that I'm taking this direction as positive, and then I'm taking this direction as positive. All right, again, go to my vectors. Now, if you're at high school, I don't think they will allow you to do this, so you must write to the right. If you're at high school, just write to the right, because at high school they don't do unit vectors. All right, so this one is for university, we do unit vectors. At high school, just write to the right. Okay, that's what you should do if you're at high school. Okay, now the question is, find the displacement. Okay, you're already given that displacement, so maybe let's say let's find t1. How can we find t1? I don't know t1. What I could do is I could find this delta t1, all right, or delta tab. So if I know delta t ab, this is going to be equals to t1 minus t0. Why? Because the time at b is t1, the time at a I said is t0. So whatever you write, you use that. If you said the time at b is tb, you write right. So you would write tb, and then you write ta if you used a and b instead of 0 and 1. I used 0 and 1. Okay, so and that is, so which means that this thing here, when I write this, I'm basically, I says which means. All right, which means what is tab? Okay, that's so I don't confuse you. So what is tab? Tab is 5 seconds. T1, I don't know, this is 0. Okay, and then which means that T1 is going to be 5 seconds. Okay, so that is important. Now if they say to you find now I want you guys to find what is it that you don't know. We found this, we also don't know delta tab, delta tbc. This is going to be, what is the final time between B and C? What is the final time? The final time is T2. So it's going to be T2. What is the initial time? I did not move from A to C. I moved from B to C. So I must take the initial time now as the time at B, which is minus T1. And that is very important because these are called intervals. A and B is interval 1. B and C is interval 2. So when you want the time between B and C, you want the time between interval 2. In interval 2, basically, that's what you want. So it's very important. And there in interval 2, the final position is C, the initial position is B. And that's very important because when we proceed, we are going to use that knowledge. All right. So this one is going to be, I don't know. This is what I don't know. And then this one T2 I know is 15. This one T1 we have found it is 5. So which means that it's going to take 10 seconds. It's going to take this car 10 seconds to move from position B to position C. All right. And then what else don't we know? We don't know what is position X2. We don't know X2. So how can we find X2? All right. And now for us to find X2, what we will have to do is we will have to say, we'll just look at, we have to choose an interval again. So what we are going to do, since we know all the information here, we are going to use that information. If we didn't know something here, then we could actually use A and C, right? You could use anything to find it. I think you'll see this as we proceed, and then you will understand how we actually do this. All right. Okay, so now from here, you have this one, T1, X1, and X2. But you are given delta X, BC, not AB. This should be BC. You're given this one, BC. All right. So since you are given BC, delta X, BC, and it's 11, you already know that this is going to be 11. I don't know why I'm putting a question mark. This is going to be 11. So let me just decrease the size of this so that I can see everything. All right. So there it is. Hopefully you can still see everything. All right. So I have this displacement here. I know it's messy now. It's not neat anymore because there's just too much here that we're doing. All right, so I have this displacement which is 11. I have x1, so x1 is 9 meters. So I don't have x2. So I can use this equation that says delta x bc is going to be x2 because the position at C, this is final, this is initial. So the position at C is x2, I called it x2, and the position at B, I called it x1. And this is very important. You must choose an interval that you're working with. So if you were working with A and C, it was going to be AC. Then it was going to be x2 minus x0. All right. In actual fact, I'm going to do something that is going to help you now understand what I'm saying. All right. Okay. Now that is that, and then this one is 11, and then this one is, I don't know, this one is minus 9. All right. So x2, you're gonna take this thing and put it this side, it becomes positive, and then I have 11 plus 9. This is going to be x2. Therefore, x2 is going to be equals to. So what I do after this, I just change. I take this side, and then I take this side, and then that's how I get to this step. And then this is going to be 20 meters. All right. So that's another one. So what happens if let me say for instance I want the total distance. All right. So what would I do? So let me just take everything out, and then I'm gonna redraw everything. So don't worry about it. All right. Now, for instance, if you were asked to find out the total distance traveled by the car, all right, or the total displacement, let's start with the total displacement. The total displacement would be delta x. Now, what is a displacement? It's a line from where you started to where you ended. Okay, so I ended at B, at C. So the total displacement would be delta AC, which is going to be, what is x at C is x2. What is x at A is x0. So I hope you guys understand. So if you wanted how, like the total distance from A to C, right, which is the total displacement, sorry, from A to C, you would have to say the final point is C, the initial point is A. Now, what is the position at C? It's x2. What is the position at A? Is x0. Okay, that's how you do it. So x2 is 20 minus here, which is 3, and then you can see that the total displacement is 17 meters. So although the distance from point O, if this is point O, the distance from point O to point C, the total distance here is 20 meters. That's what this 20 is. It is from point O to point C is 20 meters. All right. But if you look at the car did not travel 20 meters. It traveled from point A to point C, which is delta x AC, which is going to be equals to 17 meters. So this example, I like it. I normally teach it like this because I feel it just makes everything, you are able to understand everything here. All right. So you have to be careful. There's a distance that is traveled by the car, and then there's actually the distance from the observer to where where C is, right? Now, if you were to find the total distance traveled by the car, then the total distance traveled by the car would be the same because the car took the path from A to B. That was the actual path. They went from A to B. All right. So the distance traveled by the car, the total distance traveled by the car would be the same because they move from A to B. So this is going to be the same as 17 meters. All right. Now let me say, just to do something. Let me say you have this problem, but now I'm going to add another layer to this problem. So I'm making it more complex and more complex so that you are able to understand. All right. Now, let me say, for instance, you have this problem, okay? So your car moved from point A to point B, from point B to point C. Then when it go to point C, it stopped and then moved back to point B. Or that, let's say it's just turned around, moved back to point B. All right. So it got to point C, turned around, moved back to point B. So when it moved back, let's call that point D so that we differentiate. So this is, sorry, I wanted to use that. This is point D. So this is the car afterwards moved from point C back to point D. So in actual sense now, the car moved from position A, B, C, and then D. And D is in the same position as B. All right. Now, if you are then asked to calculate what is the total displacement in this case, if you were to ask to find the total displacement, what would be the total displacement? The car started at position A. Where did it end? It ended at position D. That's the total displacement. Where did you start? Where did you end? Right? So the journey started at position A. It ended at position D. So we don't care how it got to position D. So the total displacement will just be from point A to point D. We don't care how they got there. All right? And that is going to be XD minus XA. XA is 0. XD is going to be X3. So I'll call this position X3. And X3 would be the same as X1, which is going to be 9 meters, because it's in the same position, it's in the same line. If I was to draw a line between B and D, it would be the same line. So which means that in the X, this is the same position. That's how I know it's the same position. All right. So remember, I'm just interested on what is happening on the X. All right. And then XD in this case is going to be equals to 9. All right. That's the final one. Minus XA. What is XA? XA is going to be 3. Then the displacement of this thing is just 3 meters to the right, because it still moved from point A to the right to point D, but that was the displacement to the right. So hopefully you guys understand the difference. Now this is where it becomes evident why I'm trying to emphasize this. Let me say you are now asked to find the total distance, right? Remember, everything I'm writing in green is when now the car has moved. Everything in red was when it moved from A to C. The final distance was C. Everything in green, it was when it moved from A to D. And then it went from A, B, C, and then D. So it had to go backwards to D. So total distance, right? The total distance basically is just the distance from A to D. But then how did it get there? It covered, so it first went this distance, which is 6 meters. This is distance 1. And then it went the second distance. Oh, you can't see actually. Let me use, you won't see it because I'm now writing outside your screen. And I don't want to zoom it in and see. If I zoom it in, it becomes too small. That's why I don't like it. All right. Okay. Yeah, that is better now. So it moved from position A to position B. Remember, there's the original position. This is position A, position B, position D, position C, and then this is position D. So this is position A, position B, but position B is also position D. And then this is position C. Or you can write position D here. So let's look at how it moved. The actual path that it took, it went from A to B. Then it went from B to C. Then it went from C to D. So this is going to be distance 1, distance 2, distance 3. Now when you are adding the distance, you don't take into account negative. You don't do this thing of negative. So what you would do is you say the total distance will be D1 plus D2 plus D3. Okay? What is D1? D1 is a distance from A to B, and that is 6 meters because we found it. It's X. is the same as delta x AP, all right, AP. Then what is that? And you're only taking the positive values, remember that. This is the same as delta x BC D2 from B to C. Now from C to B is the same as delta x BC, just that it's in the different direction. We're moving from A to B is the same distance as C to D. The only difference is the directions. So if you were asked to find, for instance, the displacement, so the displacement from A to from B to C will be 11 meters, right, to the positive x direction, right? Or you just say plus 11 meters. You could also say it is delta B C is just plus 11 meters. So we know when you put plus, it means to the right. But if you look at delta x, at delta s, x, yes, it's x, not s. Delta x, but now it's moving from C to D. This one is going to be negative because it's moving in the negative direction, but the distance is still the same, 11 meters, because the distance from this position to this position, the size is 11, so it hasn't changed. But then when you are calculating the distance, you don't care about the size. You don't care whether something is positive or negative. So this is going to be 6 plus 11 plus 11. So it's 22 plus 6. This is going to be 28 meters. So you can see the difference. The displacement is 3 meters, but the distance is actually 28 meters. So if you were driving with a car, your car would have actually traveled 28 meters. But if you were flying, you would just cover 3 meters. That's a difference. So whenever you think about distance and displacement, the other one, think of you are flying from just that position to that position. And then when you think about the distance, is you can't fly, you have to actually take a drive, or you run, or you walk. So you have to use the road or the path to actually do that. So that's the difference between distance and displacement. So it took very long, this lecture, and the reason why I wanted it to take so long is because from now on, once you understand this, everything that you are going to do, I don't have to explain too much on it, because the fundamentals, now you have your basic fundamentals in the right place. All right. So now we are going to talk about speed. Okay. Now this is the best way I can explain speed. Now remember the example I said, I'm from my place, and then I'm running like this, then I'm running like that. This is the actual path I took. I'm going to the mall, I'm running to the mall, and then I end up here at the mall. And my distance, remember I said it was 12 kilometers. Now let me say it took me, the time that it took me about, let's just say it took me 700 seconds. All right, it took about 700 seconds to get there. All right, which is just a bit more than 10 minutes basically, right? It took about 700 to get there. That's how long it took me to move from my place, cover in 12 Ks in almost 10 minutes. So more like 11 minutes and a couple of seconds to be actual, 11 minutes 40 seconds to be actual, to be accurate. Okay, so I was in a car. You can't cover 12 kilometers running unless you are running very fast. Okay, that is my distance. So speed is actually the rate at which the distance was covered, right? So that's the speed. The speed is the rate. That is what speed is. So if you calculate it, you will find that you are calculating, you say it's equals to the distance divided by whatever time that you took. Now, this thing here is not the actual speed at each and every moment. It is an average speed. So in average, we use this. Sometimes when we don't want to use that, we would actually write av here, or some people say average like that. So it means the same thing. When they say VAV, or they say this with the bar, is average. That's basically average. So this is average. Now I'll make an example. Let's calculate this average speed. first so that I can make an accurate example. This is going to be 12. Now 12 kilometers is going to be 12,000 meters. Divide this by 700. Again, if you don't know how I did here, go and check my lectures on unit conversions and units and the metric system, and then you'll understand what I did here. All right, so we are building this knowledge. We are not starting from scratch. So this is going to be 12,000. You're going to divide it by 700. And then this is 17. This is 17.1 meters per second. All right, this is the average. Now it is possible, for instance, when I left my house, I started at 0 meters per second. Maybe when I'm here, my speed was 20 meters per second. Maybe when I'm here, my speed was 8 meters per second because I'm turning a sharp curve, I have to slow down. Then maybe when I'm here, my speed is 17 meters per second. When I'm here, my speed is 18 meters per second. Then maybe when maybe I arrive here with a speed of 19 meters per second. But look at my average. Maybe my average is just 17.1. But I had different speeds along the journey. And this is what an average is. All right. Now, don't calculate the average for this one. I'm just making an example. Maybe if you calculate an average for this one, you won't get this value. So don't calculate the average for this one. All right. I'm just making an example to say it is possible that at different points in time, you were actually changing speed. At some points you were fast. At some points you were slow. At some points you were fine, okay, a bit okay, and then a little bit faster. So it's possible that you had different speeds all the time. It doesn't mean that your speed was always 17.1, like you left with 17.1, you arrived at the mall with 17.1. So I hope you guys understand what we mean when we say that we are calculating the speed. If you wanted to find out, for instance, what is the speed here? The speed here. What is the speed here? What is the speed here? And what is the speed here? And what is the speed there? The speed at this green point is called the instantaneous speed, right? Instantaneous. How do you write tenuous? Tenuous speed, right? So that is your instantaneous speed, all right? Now that is the speed exactly at this moment. So you calculate that one differently from how you calculate from how you actually calculate what you call there should be some E, I think. Instantaneous. There should be E somewhere here, I think. There should be E. Should be like instantaneous. I think speed. Yes, I think this is the correct. Spelling. So this is not correct. Instantaneous speed. Okay. So there is a difference between instantaneous speed. The instantaneous speed, the speed at that moment. Like if you're in a car and you look at your speedometer where you see how much you're moving at, you would see 17 here. When you are here, you will see 18. When you are here, you see 19. When you're here, you see 20. When you're here, you see 8. But someone calculating, like say, okay, what was your speed throughout the journey for you to cover this distance over this time? They will say your average speed was actually just 17.1. So I hope you understand the average, the difference between the average and the instantaneous speed, because these two things are actually different. Now, how about something else? Now we introduce something else that we're going to say. Then we calculate something that we call the average velocity. All right, so now we introduce velocity. Now, what is velocity? Now, I'll go back again to that example. I start from home. Okay, use the blue one. I start from home. I travel like that. There it is. And then I arrive at the mall. And we said that the distance is going to be 12 kilometers. That's the distance. Now, when we want the average velocity, we don't use the distance, we use the displacement. Remember, the displacement is saying, let's think of you like flying. You are going to fly from this position, you're going to fly to the mall. And you find that maybe the average displacement, I'm going to call it delta S. is just going, the size of it is just going to be 2 kilometers because it's shorter. I mean, the distance from here A to B is shorter compared to when you are moving in the blue line. So when you're moving from the red, just in the red line from A to B, it's very short. So it's like 2 kilometers. Now the velocity is defined as the rate at which displacement is covered, the rate of change of displacement. You can also say that, right? How fast are you changing your displacement? The rate of change of displacement. You can say the rate at which your displacement is covered, all right, basically. Right? So how much distance, how much displacement are you covering over a certain period of time? That's the rate of change, all right? Okay. Now that is defined, the velocity is a vector, so you must put this thing, it's a vector. The velocity is given by delta S, which is the displacement over time, and this is a vector. So this one, you get a vector, so you must always have the size and you must also have the direction. You can't just say the velocity is 14 meters per second. You can't, you must tell us 14 meters per second in what direction. I'm not going to give you a direction for this one because it's complicated, right? But let's just calculate the size of it, right? Let's just calculate the magnitude. If you want the magnitude, you can just write it as V without the arrow, and then you're just going to say it's going to be delta S over delta T, and that is going to be equals to 2 kilometers. The time is still the same time. You still took 700 seconds because it doesn't matter. For instance, you took the whole time, but if someone was flying but still took the whole time, what would be their velocity? That's what we are actually calculating. So in this case, this is going to be 1 over 350, 0,003 meters per second. I'm actually, there's something wrong, guys, that I did. Sorry, 2000, not 2. Because if I do that, sorry about that. Yeah, now it makes sense actually. Because I'm thinking, for 10 minutes, you can't be. So this is actually 2000 over 700. Sorry about that. I made a mistake. I did not convert. I left this in kilometers. So this is going to be, I made a rookie mistake, as people put it. All right. So I'm fixing my rookie mistake. All right. So that's how you actually move. It's still not much, really. You're just covering 2.9 meters in 1 second. All right. So in about 10 seconds, you would have covered 29 meters. Then, yeah, and then that's how you would actually cover that time there. All right. So this is the difference between, again, you can find the instantaneous velocity because this is actually the average velocity. This is not the instantaneous velocity, it's the average velocity. So even this is still the average velocity, right? And when you write it like this, you could say, well, okay, since you're looking for a size, you could just say VR like this, which gives you something like the magnitude, all right? Okay, so hopefully you understand that. Now, it is possible for you to have a constant speed or constant velocity. All right, so if you are moving at a constant speed or constant velocity, then it's the same throughout. So if you're moving at a constant speed, you start here and then you get here. So let me say you're already moving here. We don't count. Maybe let's say the observer already, when they saw you moving at 17.1. When you are here, you're moving at 17.1. When you are here, 17.1. When you are here, so it doesn't matter where you are moving at 17.1. 17.1 meters per second, 17.1 meters per, everything is in meters per second, and you arrived here with the speed of 17.1. So this one is constant speed, meaning that it is not changing. Constant means that not changing. All right. So whenever we say something is constant, it doesn't change. That's what we mean. Right. So wherever you go, it was the same speed. if you are looking at the constant velocity, in this case, a constant velocity, remember you move from here to here, and then we found out it was 2.9. So it means that if you were to calculate what is your velocity at any point, here your velocity will be 2.9. 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 Now this is when you have constant velocity. So that's what we mean by constant speed, constant velocity, constant velocity. All right. Of course, this is not true in this case. I'm just giving you guys an example to say what does it mean when you say something is changing? What does it mean when you say something is average? What is an average? What is constant? I'm trying to give you the difference between average and constant. If this thing was constant, you would just be moving with the same speed. It doesn't matter the amount of speed. If the velocity was constant, it would just be the same velocity throughout. So now you know how to find the average. You now know what it means when you have constant velocity, constant speed, instantaneous velocity. So we have covered that. Now we go to something that students also do struggle with, and that is the acceleration. And then now we are actually picking up the pace of our course, because once we get to acceleration, we're going to do equations of motion, and then we're going to do free fall, and then we're going to do graphs, and then that will be it for this lecture. I expect this lecture to be long, maybe like 3 hours or so, but it's fine. I'll break it down for you guys on YouTube when I'm going to pick just the sections that are relevant for you, so that you can also just study whatever section you want to study. All right. Now, so let's see. Now, if you want to find out how is this change happening, right? So is there a change in velocity or not? Is something speeding up or something slowing down, right? So this is what the acceleration is going to do. So it's going to inform you whether something is slowing down or something is speeding up. And normally how you know that, if the acceleration is positive, it's going to be speeding up. If the acceleration is negative, whatever object you are looking at is going to be slowing down. All right? It depends though. So let me explain like Kevin Hart, I would have to explain. All right? Now, what is acceleration? Let's just get a simple case of what is acceleration. All right? Now, again, the acceleration that I'm calculating now is the average acceleration. It is not to say that the acceleration is the same throughout, right? I'm just calculating the average acceleration, okay? The average acceleration is given by change in velocity over change in time. So what does that mean? Let me say I have an object here, and after some time, my object is somewhere here. So my object moved from point A to point B. When my object was point A, my initial time was 0 seconds. When my object was at point B, my final time maybe was like 6 seconds. Here, my velocity was 0. V0 was 0 meters per second. It started at rest. Then it started speeding up, and then my final velocity was something like 14 meters per second. So you can tell from what we did before, you can find out what is the change in time. The change in time, if you calculate it, is going to be 6 seconds. All right? I'm no longer going to show you these things because I spend almost an hour, over an hour, telling you and describing how you find these things. Right? So if you want to find the average acceleration, right, I'm just going to call it A. If you just want to find A, which is a vector, by the way, all right? So it's going to be given by change in V over change in time. Now remember what change in V is the final velocity minus the initial velocity. Now the signs are very important here. So if the final velocity is pointing to the left, you must put the negative. If the final velocity is pointing to the right, you must leave it as positive. All right. I'm always using this Cartesian plane. So I will not tell you. I always assume up is positive and then right is positive. All right. So I'm always going to do this, and then I'm not going to change. I will tell you when I change. All right. Then the final time minus the initial time. All right. So in this case, if I wanted to find acceleration, what is the final time? The final velocity. Final velocity is v1. Initial velocity is v0. And then this is t1 minus t0. Okay. So this is how I'm actually going to find the acceleration. And then what is that acceleration? Well, the final one is 14 minus 0. The initial is 6 minus 0. So this is 14 over 6. Therefore, the acceleration is 14 divided by 6, which is 2.3 meters per second. So remember, the acceleration is the rate of change of velocity. Right? How fast? The rate is how fast. How fast is velocity changing? So it's the rate of change of velocity. The velocity is rate of change of displacement. How fast is the displacement changing? And then the speed is the rate of change of distance. How fast is the distance changing? So the word rate says how fast. So, and how fast is always related to time. Okay. So this is how we find acceleration, and this is how we can actually calculate acceleration. Now, there is another concept whereby something is possible for something not to accelerate. So what happens, for instance, when something is slowing down? All right. Now, let me say, for instance, I have an object. So first time when I measured this object, the time is equal to t0. I found out the velocity of this object was 20 meters per second. After some time, this object, maybe after 8 seconds, I measure the velocity of this object. And now this object is actually moving at 9 meters per second. So you can see that this thing is actually slowing down, right? Now we can find acceleration for this. So if you find acceleration for that, which is a vector, and I forgot something here, and it's very important that I teach you that. It is very important that you actually find the direction. So you must specify the direction, which is to the right. How do I know that is to the right? Whatever the direction, this object was moving this way, and this object here is still moving that way. So you can say that the direction of change in V is going to be that way, right? How do I know that? If I was to find change in V, it's going to be 14 minus 0, which is 14, and 14 is positive. So since 14 is positive, it means that it's moving to the left. All right. So you'll see, for instance, with the example that I'm going to do now, and then that whatever the direction of the change in velocity is, that's the direction of the acceleration. Not the change, not the direction of velocity, because this one here, if you look at it, it is still moving in that direction. And here, it is still moving in that direction because it's still positive. So velocity is still positive. Here, it was, okay, it's 0, but then it started moving in that direction. Okay. Now, which means that the object is actually moving in this direction. But now, what is going to happen with the acceleration? Well, with the acceleration, it's going to be change in V over change in time. Okay, so what is change in V? The final velocity minus the initial velocity. All right, and then this is the final time minus the initial time. Now, what is the final velocity? Is 9. What is the initial velocity? Is 20. And then what is the final time? It's 8. What is that? This is 0. So you already have minus 11 over 8. So you see there's a minus. If you were to find the change in V for this, it's going to be V1 minus, guys, please go and do vectors, because when you do vectors, this thing makes sense why I'm saying this is a vector, this is not a vector, and how I'm writing things. So you won't understand if you don't follow my vectors course, and it's going to confuse you. All right. So this is V1, this is V0. What is V1? V1 is 9, this is 20. You can see that this is negative 11 meters per second, which means that my change in V So my change in v is pointing that way, but my object is moving that way. So there's a difference here. So my object is moving to the right. This is where my object is moving. But my change in v is actually to the left. So these things are, this is direction that the object is moving. This is the direction of the object. Direction of the object. All right. Now this one is the change. So here the acceleration is that, and then let's just calculate it quickly before I explain a lot of things so that I don't confuse you. So this is actually going to be the acceleration. It's a vector. It is going to be 1.4 meters per second squared to the left. Now, what does this mean? If you have an object and the object is moving in this direction, and also the acceleration of that object is moving in the same direction, then this object is going to speed up. Think about it when you are in a car. When you want to make your car faster, you press the accelerator. That's why it's called the accelerator, right? You accelerate. When you press the accelerator, the car speeds up. What happens if you see something or you had a robot you want to stop? You press the brake. What the brake is doing is stopping the car, so it applies something that we call a force. We'll get to forces in the different direction, meaning that it's changing the direction of the change in velocity. So meaning that if I have an object, it is moving in this direction, but my acceleration is in that direction, which means like this one is negative. I mean, this is to the left, that's why it's negative. You could also write this and say it's just negative 1.4 meters per second squared. So if you put a negative, you don't have to specify the direction because we know this negative means the direction. If you don't put the negative, you have to tell us the direction. So that's the difference between the two. This one, you have an object moving to the right, but the acceleration is negative. And then in this case, we have a case of, they say the acceleration is actually, when it's negative, we call it deceleration. I think it's that deceleration. Right? So this is deceleration. Okay. Now I'm gonna erase this one. So this one is actually going to slow down. And this is very important. When the acceleration is in this direction, it means that the change in v is that direction as well. And then here, the change in v is that direction. So whatever the direction, the change in v direction is going to be the direction of the acceleration. Whatever the direction of the acceleration is going to be the direction of the change in velocity. Students get confused a lot when you actually ask these questions, and this is where you'll be surprised when you ask students to calculate complicated things because they've practiced, they get it. But when you start asking understanding things like this is where students just don't get it, and they actually fail because they don't understand the actual concepts of these things. All right, so this is how you can actually know something is accelerating. This is how you can know something is decelerating. Now, decelerating doesn't mean that the object has changed direction. Doesn't mean that. It just means that the object is going in the opposite direction to the acceleration vector. That's what deceleration actually means. The direction of the object hasn't changed. If the object was moving to the right, it will continue moving to the right, but it's going to slow down. This is the same thing like you're in a car and then you are approaching the robots. When the driver applies the brakes, the car doesn't change direction. It continues to move towards the robots, but it is slowing down. When you're accelerating, it is moving towards the robot, but is speeding up. So deceleration means slow down. Acceleration means speed up. That's basically what you can actually think. That's how you can actually think about these things. So hopefully you guys understand that, right? So it is possible to have a case whereby your acceleration is constant, all right? Which means that your acceleration is not changing. And generally this is the case. For instance, the acceleration that we actually calculated here is not changing, it's constant throughout, right? So we are not changing acceleration. If you think about it, if you know how to drive, when you put your foot on the accelerator and you don't press it and or you don't bring it towards you, you just have your foot stand there and your car keeps speeding up, but your foot is not moving. So meaning that you are keeping the acceleration constant, but your car keeps speeding up. And so this is the case when you are actually calculating this average acceleration. You are keeping your acceleration constant. It is possible to have acceleration that is not constant. All right. And I think in those cases, I'm going to deal with that where acceleration is changing. I am going to deal with it in a case of equations of motion, where you have in one section the acceleration was something else, in another section the acceleration is something else, right? Or intervals. It's changing with intervals. It is also, for instance, so the force on the spring is changing, the acceleration on the spring is actually changing. So you can have actually a varying, so whenever you have a varying force, you have a varying acceleration. If you're in grade 12, you haven't done these things, don't worry about what I'm saying now. From here, I'm going to talk about something that we call equations of motion. Okay? Now I'm going to talk about equation of motion. This is like the moment of truth for a lot of students. This is, I can guarantee you, when you are getting tested on this section, you're mostly going to encounter problems of this nature. All right. I am not going to derive the equations. I am going to just list the equations. And then after listing the equations, and then I'm going to show you the situation. Then after showing the situation, and then I'm going to do them in the x direction. Then I'm going to do them in the y direction when we do free fall. And then I'm going to just apply them on whatever equation. So I'm going to apply them on a question whereby we have different situations. I'm going to apply them when we have just a constant acceleration. I'm going to talk about something that we call reaction time. I'm going to give you a situation whereby you have simultaneous equations, whereby you can use simultaneous equations. And yeah, then I'm just going to look at those three problems. Then I'm going to go to free fall, so when something is falling or not falling. All right, so that's what I'm going to do when it comes to these equations of motion. So let me assume I have an object. It starts at rest. Okay, let me not say it starts at what. So the time here is t0 and the time here is t1. Okay, let me say t initial and t final. So it's moving from initial position to final position. And then the velocity here is the initial velocity, the velocity here is the final velocity. Now the distance from here to here, I'll call it delta x. And the time from there to there, I'll call it delta t. So whenever I use delta, it's something from somewhere to somewhere. That's where I use delta. But whenever I don't put delta, this thing is delta, this change is called delta, right? So when you hear me saying delta, that's what I mean. I mean this triangle here. It's called delta. Delta is also used to say change in whatever, like change in x, change in t, whatever, right? So that's what delta is. All right. Now, what I'm assuming, I can only use equations of motion if there is acceleration and the acceleration is constant in that interval. It can change in different intervals, but you can only apply equations of motion in that interval if A is constant. All right. So these are vectors, these are not speeds. All right. Now, what are the equations of motion? The equations of motion are saying that I can actually find the final velocity. It is going to be equal to the initial velocity plus the acceleration change in time. Okay. And then some people will write it like this: V is equals to v0 plus at. So what they are doing here is where I put delta t, they just call it t. Where I say initial is v0, then where I say is final, they say v. So this is fine. Don't get confused, right? I'm showing you like this so that you actually know exactly what is what. All right. Also, you can find the final velocity squared, initial velocity squared, plus the acceleration change in x. There must be 2 here. Change in x, this is the displacement. Remember, when it's negative, you must put negative. When it's positive, everything, the displacement, the velocities, when it's negative, put negative, positive, positive. You can also find the change in x if you know the initial velocity multiplied by time plus half the acceleration times squared. All right. Also, for these two intervals, you can actually find the average velocity. All right. So I think how I'm going to do this is I'm going to say I can find this delta time. It is going to be half the final velocity plus the initial velocity, which is the average, velocity multiplied by delta t. Okay, so this equation here comes from the average, right? This is using the average velocity, right? This is where this equation comes from. These are the 4 famous equations of motion. All right, so now we can just apply them in different situations and then see how we can actually use them in a problem. Remember, the acceleration must be constant in order for you to apply these equations of motion. All right, so this is very important. Okay, all right, so what you can show is you can just come up with an example. I'm not going to write it, the problem statement. I'm just going to say the problem statement as I'm drawing it. Okay, so what I'll do is you have a car that starts at rest, right? You're going to have a car that starts at rest, and then it accelerates, let's just say maybe to 25 meters per second, covering a distance of, so it starts at rest, so v0 is going to be that, and then it accelerates up to some velocity, and then I said it's going to be 25 meters per second. That's a lot. And then it then continues moving at a constant speed. So it's going to move at a constant speed, and then we're gonna find out what is that speed. So when it starts at rest, so you have a car that starts at rest and then accelerates to 25 meters per second, covering a distance of 1.8 kilometers, 1.8 kilometers, and then it then moves at a constant velocity for 1.6 hours. Okay, so it's going to move at a constant velocity for 1.6 hours. That's basically what is going to happen here. Okay, so this is a very good example of how we can actually use equations of motion. So what I will do is this part, the second part, I'm going to have it as red so that you understand what is happening here. All right, so I'll have the green part and then I'll have the red part. Now each part is an interval. Okay, so the car initially moves from point A to point B. Something happens when it moves from point A to point B. What happens? It started at a speed of 0 and then it's speeding up. Okay, so here it is actually speeding up. How do I know it is speeding up? Because it started 0 but now it has some velocity here. All right, so if it is speeding up, there is acceleration, right? So there is acceleration. Let me use the green color. there is acceleration, and let me just have A as green as well. Okay, so there is acceleration here. Now, do I know that acceleration? No, I don't know acceleration. Do I know how long it took to move from this point to this point? No, I don't know. So you must start immediately putting things that you know and things that you don't know. Right? I only told you the values that I gave you. What I do know is that it covered a distance from A to B of 1.8 kilometers. So I can say the magnitude from A to B is going to be 1.8 kilometers. And then, okay, so, and then afterwards it moved with a constant speed. So, and then I'm told that it's moving at a constant speed. What does constant speed mean? Constant speed means that, so since the speed is constant, it does not change. So it does not change. Okay. All right. So here on the red part, which is from B to C, the car is actually moving at a constant speed, and that constant speed, it doesn't change. So which means that once it reaches 25 meters per second, the speed is going to stay 25 meters per second because it does not change. I mean, if it has to be constant, remember what I said about constant speed. It's 25 here, 25 here, 25 here, 25 here, 25 here, 25 here. So once it reached 25, it didn't change. So it became 25 meters per second all the way up. All right. So this is how we are going to solve this problem. I am going to break it into two sections. So I'm going to solve A and B, and then I'll tell you what I'm looking for between A and B. All right. Now let's just focus on A and B. From A to B, what is happening? This is from A to B. And then afterwards, we're going to do B to C, and then we're going to combine everything. What is happening from A to B? It's starting at 0 meters per second. So you should be able to break a problem up like this. Then this is V1, 25 meters per second. Okay. And then it is, what is the time here? Now, this is where the observer is. Now, the person that says, it says that the car starts at rest. Now, they don't tell us how far the car is when they start describing the motion. Now, this is only when it is very good for you to assume that the car and the observer are in the same position, they are in the same spot. Now, if the car and the observer are in the same spot, then you can say x0, you can assume that x0 is going to be 0 meters, which means that the car is where the observer is. Now here, x1, I can get x1 because I am given xab, so I know the distance from A to B, which means that I can actually change that distance. Okay, maybe we're gonna calculate that one. Maybe let me just keep it like that. We're gonna calculate it, is fine. I'm gonna ask you guys to calculate it. Do I know change in time from A to B? I don't know. Question mark again. I don't know. They didn't tell me how long it will take to move from point A to point B. Do I know the acceleration? I know it's gonna speed up because it's moving from 0 to 25, but do I know the acceleration? I don't know the acceleration. So hopefully you guys understand how I'm breaking the question up. And now, do I know the distance that it covered from A to B? Yes, I know. This is the distance. So this is delta x AB, which is going to be 1.8 kilometers. Now, 1.8 kilometers, just change it into meters because you have meters here, you have meters here, you have meters here. So change this 1.8 to kilometers. So again, from chapter 1, you're just going to multiply this by 1,000. Then this becomes 1,800 meters. So it covers a distance of 1,800 meters to move from here to there. All right. So this is it. There's nothing more except time. So the person had a stopwatch. So what was the stopwatch of the observer when it was here? It was saying 0 seconds. What was the stopwatch when they were here? Don't know. All right. So when they were here, we don't know. T1, I don't know. So you can guess. The question is going to ask you to find everything that has question marks. So we're going to find everything that has question marks, and then we're going to proceed from there. All right. Now let's find everything with question marks. So we are going to start with the easiest one. Okay. Now, how do I know which one is going to be the easiest one? This is how you know. Let me say, for instance, you decide to find change in time from A to B. So you're going to write all the equations that are going to give you change in time from A to B. One equation is going to be the final velocity V1 is going to be V0 plus the acceleration change in AP. Now here's the problem. I don't know this, so I can't use this equation. So this is wrong. At least in an equation, you must only have one unknown. So here, I don't know two things already, so it's not a good equation for me to use. All right, let's see. Can I find the acceleration? Can I find the acceleration? I can find the acceleration. I can use any equation that doesn't have time. One of the equation is this one, because any equation with time is gonna give me the same problem. So this equation plus 2a delta x a b. So let me see. I have this, I have this, I have this. The only thing I don't know is this, so I can use this equation. So I know I'll find the acceleration using this equation. All right. So okay, so can I find T1? It's difficult to find T1 because for me to find T1, I'll have to say delta TAB, which is going to be T1 minus T0. I know this, I don't know this, I don't know this, so I can't find this yet. All right, so I can't use this equation yet, I can't use this equation yet. Immediately an equation has two unknowns, I can't use it. Let me say I wanted to find x1. How would I find x1? Well, I can find x1 from delta x AB. That's how you always find time. And whenever you are asked to find a distance at a particular position, you're going to use the displacement. Whenever you are asked to find the time at a particular position, you're going to use the change in time always. So you need to know this. All right. This one, I'll need x1 minus x0. Okay, I know that, so I can use this equation to find x1. So this equation again is good. So I can find x1 easily, I can find the acceleration easily. The one that is not going to be easy for me to find is delta TAB, and therefore for me to find delta TAB, I will need at least to know the acceleration, then I can find delta TAB, right? Another equation that can give me delta TAB is the one that says delta x AB, which is the distance from here to here, is going to be equals to V0, there's V0. Remember, I'm using the four equations, right, of motion. V0 delta T AB plus half A delta T AB. Now, the issue with this one, I don't know this, I don't know this, don't know this, I know this, I know this. So already there's two things I don't know already. So you want to just have a situation whereby you don't know one thing. So I can't use this as well. So that is how you actually choose or know which one is going to be easier for you to find and which one is not going to be easy for you to find. So once you master breaking things up into small segments like this, and you can see now I've avoided this one from B to C. It's like I'm assuming, it's like it doesn't exist. I'm not even thinking about what is happening here. I'm just focusing here, right? I'm just focusing here, and I'm trying to find everything that I can find here. All right, once I have everything here, I will add that information, then I can start solving for whatever it is that I don't know here. Okay, so it doesn't matter what the question is going to ask you. I can guarantee you they are going to ask you the things that you don't know, whatever you put question marks on. So if you master how to model your problem, put the question marks, they can't fool you. You know what they're gonna look for. and you will get it because you will know how hard it's going to be to get something and how easy it's going to be to get something. So that's very important for you guys to understand that. All right. Okay, so that's good. Now let's see. And then now I have this AP. I'll come back and then do BC. All right. In actual fact, I'll just erase everything here. And then I'll do that. So let me make sure that everything is showing on your screen. Okay. So let's find A. So we're gonna use this equation. Now I'm gonna use a different color. So we're gonna use this equation to find the acceleration. So we're gonna say V1 squared is going to be V0 squared plus 2 A delta X AP. So if you decided to call delta X AP, I would encourage you, like if you put 1 and 2 here, call it delta T1, 2. If you put A and B, call it delta T A B, or you could say delta T1, delta T0, but you must make sure that you are telling whoever is going to mark your paper, what are you calling what? You can't just have V everywhere. Like, what is the velocity here is V. What is the velocity here is V. What is the velocity here is V. You can't do that. It's delta T here, delta T on the second interval. You can't do that. You must make sure that when you name things, they are separate. Okay. This one, because it's the first interval, I'll name this acceleration 1, right? I'll put 1. This is acceleration between A and B. So I'll call it acceleration 1. So I'll put 1 here. I'll put 1 here so I know which acceleration am I talking about. I'm talking about acceleration from A to B, right? I don't know whether this acceleration is going to continue from B to C or not, right? So, but at the moment, I don't care about that. I'm just making sure that everything is from A to B. So I'll call it A1. If it continues, it's fine, we're going to continue. But if it doesn't continue, then we have to call the acceleration between that something different. Okay, so what is the final velocity? It's 25 squared. What is the initial velocity? Is 0. 2, do you know A1? I don't know A. What is this? 1800. Okay, so I'm hoping you know how to solve this, right? This is going to be 25 squared. I don't know what is that value? Actually, let me just calculate it. I'm trying to do this step by step so that I don't lose anyone, because students get lost when you start making everything the subject of the formula. So this is going to be 25 squared, and then which is going to be 625. 625, yeah, it's 625. I'm forgetting these things now. All right, and then so what you're going to do here is you're going to take A and put A. You're going to take A, put A in front, so it becomes A1. Then you are left with 2. So this 2 comes here, and then 1.8. All right. And then this becomes 625 is equals to A1. Then this one, if you multiply it by 2, it becomes 3,600. Okay. So this is the same as 3,600 A1. Okay, now before people get confused, I have now 265 is equals to 3,600 A1. So what I did was I took this 3,600 and put it in front of A1, and then I got this. All right, so remember the left hand side is going to be 625, and then the right hand side is going to be whatever it is that I'm simplifying, which is that. So to find A, I am going to divide both sides because I want A, so I have to divide both sides by this. So I'm going to show you here on this problem, and then afterwards I'm not going to show you the mathematics. And then A1 is going, now this one is going to cancel, so I'll be left with A1. So let me not confuse you. So 625 over 3,625 divided by 3,600, this is going to be 0.170. In actual fact, let me erase everything. It's slow, my computer is slow, I don't know why. All right, and then this one is going to cancel, and then I'm going to be left with A1. So you found A1, so which means that this thing here is actually going to be A1. So now I can put the unit. Now, since it's positive, it's going to the right. Okay, so just leave it as positive, or just write it. Just when you write it, just say positive 0.17. All right, this is going to be meters per second squared. That is A1, and it's going to be positive. All right, so that should be good. Now let's see if I did everything correct. This is 25 meters per second. Then 1.8 multiplied by 1000 is going to 1800. 2 times 1800 is going to be 3600. Yes, I'm right. And is the equation right? Yeah. Then you square that. Yeah. So everything should be fine. 25 squared is 625. Yes. All right. So everything should be fine. The acceleration is not that big, but there is acceleration. Okay, that is good. So that's how we found A1. Now we said the another one that is going to be easy for us to find is X1. So we want to look for X1. How are we going to find X1? Going to use the equation that says delta XAB is X1 minus X0. So just make X1 the subject of the formula. Okay, since most students prefer to do this, substitute. I love doing it, just the math substitute at the end. That's how I was trained. But then I realized that students are not trained like that, and they don't like it when you do that. You confuse them when you do the math and just substitute everything at the end. So it's fine. What I will do is I'll just substitute the values, right? Delta XAB, and that was 1800, 1800. And then this is X1. I don't know X1. This is 0. So which means that X1, now I'll just take this X1, put it this side, take this, put it this side. So you'll see me doing this a lot. So whenever you see me swapping them around like this, just know I took this one, put it this side, took this one, put it this side, and then I end up with something like this. All right. So from now on, I will start doing this. So you shouldn't be confused when X1 was this side and then all of a sudden X1 is this side. What happened to 0? 0 is 0. So it's like nothing. So that's why I just removed it. It doesn't matter, right? It's like it's not there. It's nothing. You're minusing nothing. So you shouldn't even care about something that is nothing. Now, given that we have the acceleration, since now we have the acceleration, I know this, I know this, I know this. Now I can find this. All right. Now, how can I find that? And now I can find that, and that is going to be given by, right, it's changing the colors. And all right, so I'm going to say delta A B, and that is going to be equals to T1 minus T0. All right, and what is that? Okay, so what is T1 minus T0? All right, this one I don't know. T1, I'm using a wrong equation. That's why I'm like, what's happening? All right, so I'm actually using a wrong equation. I can't use that equation because I still have two unknowns. I don't know delta T, and I also don't know T1, so I can't use that equation. All right, so the equation that I can use is the one that says V1, because I know V1. You always use what you know to find what you don't know. A1, I know A1 now, so delta T AB. Again, I would have just done this in one step or two steps, but then just so that I explain and everyone understands, I'm not going to do that. All right, so what is this? This is going to be 25. This is going to be 0. Then this is going to be 0.17 delta TAB. All right. All right, that's fine. That's good. And then this is going to be 25. 0 goes away. This is 0.17 delta T AB. And then now from here, for instance, if you're doing like metric and they say show your work, they may want you to show steps. So you may have to show all of this. But generally, they shouldn't penalize you for just doing the maths and substituting and then getting an answer. They shouldn't penalize you. You have shown all your steps, right? But then you'll never know. So what you do now is divide both sides because you want to be left with this. So you divide both sides by 0.17, 0.17. So this is going to be big. So, and then what you end up with, I don't want to swap them around because it's going to confuse people. So you end up with 25 divided by 0.17. This is very small. It's very small, right? But you end up with 147 seconds is going to be equals to delta AB. All right. Okay, so this should be fine. I should put a square here. I forgot to put a square there, right? So you should put a square there. Okay, so this is it. Once a green color for BC. All right. Now BC, remember you're joining it from here to here. This is BC, and then you have information. But what I'm going to do is I'm going to take this section of BC out and just focus on it separately somewhere here. In actual fact, let me draw it here so that I have some space. So I'll draw it somewhere here. So I'm going to let's do this. I'm going to draw it somewhere here. Okay, this is going to be B, this is C, right? Don't confuse it just because it's next to one another. I'm just making space. All right, just forget about this, like this is on this side. All right, so I'm drawing a new one here. All right, so what do I know about BC? I know that V1, since it was constant, is going to be this, so which means that V2 is going to be 25 meters per second. I know that because the speed is constant. All right, what else do I know? I know that it takes the delta time from B to C. They said that is 1.6 hours. So let me see if that is correct. Yes, it's 1.6 hours. Okay, so this is 1.6 hours. So I have to change these hours into seconds. So what you do, just take this 1.6 multiplied by 3,600, and then it's going to go into seconds. All right. So, okay, I'll do it down there. Right, what else do I know? Well, since the speed is constant, now we're going into something that is very important. What is going to happen to acceleration? So let's call the acceleration between B and C A2. Do I know it? I don't know it yet. I can find out. Now, if you look at it, the object is not speeding up from here to here, and it is not slowing down as well. It's just maintaining the same speed. Now the question is the acceleration or not? So let's see how we can find acceleration. So we know that delta BC is going to be 1.6 hours. You're going to multiply this with 3,600 seconds divided by 1 hour. The hours are going to cancel. So you are left with 1.6 multiplied by 3,600, and then this actually becomes 1.6 multiplied by 3,600. This becomes a lot of seconds, 5,760 seconds. All right. So that's the time that it took to move from B to C. Okay. Now, if I want the acceleration A2, remember how we find acceleration. You say change in V over change in T. So what is changing? You're looking at a change in T from B to C. So it means change in V from B to C. Now what is that? Of course, it's a vector. Everything is a vector here. So what is that? Now the final velocity at C minus the final velocity at the initial velocity at B, right? Which is the velocity at B. This is the time at C minus the time at B. So the time at C is T2. All right. I don't know the time at C. I don't know that, but I know this. So that I can actually make it easy. Since I know delta T BC, let me not break it down, because if I break it down, I have to find out what is T2. I don't know what is T2. I have to find out what is T1. I don't know what is T1. All right. Well, I know what T1 is at the moment. Okay. T1 is this 147. All right. So let me just erase this. All right. And then I'm using the green color. I'm going to leave this delta BC because you know it. If you know it, don't break it down. Now, what is VC? VC is 25, the velocity at C. The velocity at B is 25 as well. And the time here, the change in time is going to be 5,760. This is going to be 0 divided by 5,760, which is 0 meters per second squared. Now, whenever the velocity is constant in that interval, it is not constant from A to B, it is only constant between B and C. So you have something that there's acceleration, there's acceleration, there's acceleration. When they get to point B, they remove their foot from the accelerator and then they just allow the car to move at a constant speed. So there isn't any acceleration there. Of course, you're assuming that the road is straight, there is no friction, then it's going to move at that constant. Otherwise, you would actually maintain the acceleration such that it doesn't speed up, it doesn't slow down. All right. So what is important is that your car is not speeding up, it's not slowing down. Here it's just moving at the same speed. When the car is moving at the same speed, it means that you are not accelerating, you are not decelerating. That is what these 0 meters per second mean. So which means that whenever v is constant, it doesn't matter. You don't even have to calculate it. It means that the acceleration in that interval is 0 meters per second squared. Right? It doesn't. You don't have to calculate it. I calculated it so that I can show you why it is 0 there. All right. Otherwise, going forward, you don't need to calculate it. As long as it's constant between that interval, then you don't need to calculate it. All right. Okay. So let us now continue putting values. So I'm gonna erase this. I'm going to erase that and that and that, and then I'll continue putting values. I don't know that. Do I know that? And then x1 here. Now I'm writing with an eraser. Do I know x1? No, I don't want it to be blue. I want it to be green. Do I know x1? I think I do know x1. It is 1,800 meters. So you're taking it from here. The distance at B is 1,800 meters. Do you know T1? Yeah, it's this one, 147. So you're continuing from there. It's 147. Now, do you know the time here? You don't know it. So you don't know the distance here. X2, you don't know. Do you know the time? You don't know. Here at 2, you don't know. And that will be the total time. Whatever time you get here at T2, that is the total time for the trip from point A to point C, because that will be the time at C at the end. So you started counting here at 0, then you end counting there. So that will be the total time, whatever time you find at C. But don't worry, whatever answers I find here, I'm going to replace them here, and then everything can make sense in the full diagram. So what do I have now? I don't know that. So which means I don't know also the delta x from B to C. I don't know it. So what did I tell you? Everything that is question marks, that's what the question is going to ask you. To probably find the total time, find the total distance, find the acceleration between B and C, find the displacement between B and C. These are the things that they are going to ask you. So I didn't want to put it into words because it's going to make the lecture very long when I have to do, like I'm breaking down the problem statement. So I just wanted to teach you how you analyze it once you have it broken down. All right, now from here, let's just find A. We already found A2. So A2 is 0 meters per second. So which means that now, since this thing is 0, we don't need to use any equation with A. So any equation with A, we don't need to use it. So which means that the equation that we can use here, we can actually use this equation from B to C. It's half. What is the final at C? The speed is V2. And then here it is V1. You can also say V1 plus V2. It's up to you. It doesn't matter because there's a plus sign here. All right. Multiplied by delta time from B to C. So you can use this equation. All right. Basically what this equation is saying that the average velocity, right, the average velocity from B to C is given by delta x, B to C, over delta t, B to C. Instead, when you do average, if you have 2 points, for average, you just say, take those 2 points, divide them by 2. That's what you're actually doing. All right. Don't worry too much about that. If you don't understand it, it doesn't matter. Just know how to use it. All right. So for instance, I do have the time. and I don't have the total distance, but I have the velocity, so I can find the distance. All right. So what is the average velocity? So for instance, let me find delta x bc. So delta x bc is going to be half, and then this is 25 plus 25. It was going to be 25 anyway, multiplied by the time, which is going to be, I said this time was what? I think I said it's going to be 5,000, 5,760. I think that's what I said. So this is going to be 5,760 seconds. Okay, this is second. So you're gonna put the time in seconds. Remember, you convert everything into meters and seconds. All right, again, go to chapter 1 where you did conversions, units. I showed you guys what are SI units when I spoke about quantities and all of those things and units, right? So you can't do this chapter. I've structured everything so that you can actually proceed from the initial videos that I had. All right. Okay, so when you calculate this, you just put it on your calculator. This is just going to be, for those of you that maybe this is going to be half of 50, which is 25 anyway, and then 5,760. But again, I'm showing you because I need to show everyone. So this is half, you multiply it by 50, which is 25. You multiply it by 760. And then that is that. The distance is very, very, very long. Okay, makes sense though, 100 and something kilometers. So it's 144 kilometers, which is 144,000 meters. But this is kilometers, like it's 144 kilometers. So it makes sense for that journey. It makes sense. I mean, if you're gonna travel 1 hour something, you must travel 100 and something kilometers. Okay, so that is fine. So that is the distance. So now I have this the distance. What else I don't know. I have this one. I found it is 0. I found this one. Now I can find what is x2. How can I find what is x2? I'll say delta bc is going to be x2 minus x1. When you want c, don't say delta bc is going to be this minus that. Your initial changes, because you are now looking at this interval, which means that this is the final point, this is the initial point. When you are working with this interval here, this is the initial point, this is the final point. If you were working with the whole thing from A to C, this will be initial, this will be final. But you can't use equations of motion from A to C because the acceleration here is changing. There's acceleration here, and then there is no acceleration here. So you can see that the acceleration is not constant from A to B to C. It's changed. So you can't do that. That's why it's always going to help you to break things down like this, right? So that you avoid making those mistakes. All right. So I have this one. This is 144,000. And then I don't know this one x2, but then I know this one is 1,800. Okay, so if you solve this, I'm taking now, you should know how to solve it. If you're in metric and university, you should know how to solve this, right? Just take this, put it this side, and then it becomes a plus. So you just add that, and then you have 1,500 145,800. Yeah, that's basically how you read it. All right. Okay, so this is good. This is very good. So you have x2, and then there it is. All right. Now, I have that. I have that. Now I need to find what is t2, the total time. Now you can also find t2. I don't think it's going to be very difficult to find. So let's just move everything up a bit. Yeah, let's just find it here on this small space. Because I already know what is delta t bc, right? This is going to be equals to t2 minus t1. I already know what is t1 and I don't know t2. So this means that where I see delta t, all right, let me just do it underneath so that people can follow and then I don't confuse anyone. So where I see this, I'm going to put 5,760 where I say T2, I don't know T2. T1, I found it as 147 seconds, all right? So you solve this by taking this guy this side, and then you end up with T2 is going to be 5760 plus 147. Then this is 5,907 seconds, all right? So that's what you will find. Now I have everything that I didn't know there. So now I can come back here and actually populate it, all right? So which means I can actually say my acceleration A2 is going to be 0 meters per second squared. That's what I found. My final velocity V2 is going to be 25 meters per second. My x2 is going to be, what was the total distance? 145,800 meters. And then t2, which is that total time that I just found, it is 5907 seconds. So you can see now I know everything about this. If I wanted to find out what is delta xab, this is 14400 meters, and then the time I'm giving the time between B and C, not AP, this is B and C. This is going to be 5760 seconds. Okay, it's not neat anymore because I'm just doing everything, but this is what it means. So this is how you actually analyze equations of motion. All right. So there is something that we call reaction time. All right. There's something that we call reaction time, whereby you are given a problem and then you are told there's a reaction time. So how do you deal with that problem when you are told that there's a reaction time? All right. So a typical example of this, maybe let me just write a problem statement of this and say, okay, let's just break it down and then we can define what is it that we want to find. All right, let's just break the question down before we define what we want to find. Now, the most important thing here is not to calculate everything. I just want to show you how you use the reaction time. So how do you draw this, and then how do you do this? All right. So what is happening here is you have a situation whereby you have a driver that is moving from rest. Starts here. V0 is 0 meters per second. They drive. After 18 seconds, they are somewhere here. And their speed when they are somewhere here is 14 meters per second. So how long did it take to move from this point to this point? It took them delta t. Now I'm going to call it delta t1. And then it just took delta t1. And then I'm still going to call it point A, point B. I'm just changing the notation so that you don't cram A and B. All right, it took 18 seconds. Okay. And then he sees the robot is going to change, but then he doesn't apply brakes same time. So for some time, this car is still going to move at that. Then it's going to apply the brakes at this point. Okay. So when he applies the brakes at this point, what is the velocity here? That is what we'll have to calculate. All right. Then afterwards, he applies deceleration. And then this is where the robot is. And then they are going to stop here, the robot. Okay, so that they stop somewhere here. So that is at point B. So here they will stop. This is V3 is going to be 0 meters per second because they will stop when they get here. All right, they will apply brakes here and then they will stop there. All right. Now, this section here, this is when you see a robot, but you take time to respond. That is what the reaction time is. How long did you take before you could respond? So let me say, for instance, you can see that something is going to hit you. If I take 1 second extra before I move, so my reaction time was I saw it, but then I only reacted after a second, right? So this one, he sees the robot. When it's here, he can see that the robot is changing from green to orange. but he doesn't apply brakes here. He only applies brakes at this point C here. So which means that there's a gap between him seeing the robot and him applying the brakes. And that is what the reaction time is. Now the question is, before he got to see what happened to the car was still accelerating, right? So it's very important to understand that the car is still accelerating, which means that the acceleration that he has here, which is A1, is still the acceleration that he will have here between A and B, because he didn't change acceleration. Remember, he just moved from 0. He was busy speeding up, speeding up, speeding up. So which means that here the speed was 14, but here the speed is going to be something higher than 14 because he kept accelerating. So basically from here to here, he was accelerating with an acceleration. Let's call that acceleration A1. Why I'm calling it A1? Because it's going to be the same from here to here, because he did not do anything between B and C. He did not apply brakes. He did not leave the accelerator. His foot was still in the accelerator. Even though he was still deciding what to do, but then he did not leave his foot and then took off the foot from the accelerator. And that is what is happening here on the reaction time. All right, so let's just find what is going to be the final velocity here. All right, so in order for us to find the final velocity, again, we're going to break it down. We don't care what happens after he applies brakes. In this case, we don't care. All right, I think we have all the information except the fact that here, let me use a different color. Here, the acceleration is different. It's going to be 3.2 meters per second squared. And here you will notice that the car is still moving in that direction. But what is happening is that it is slowing down. So the car is still moving in that direction, but the acceleration is that direction. So it is slowing down. That is why eventually it comes to a stop. It stops because it is being slowed down by the brakes. So the brakes are actually the deceleration that is happening on the car. All right. Okay. Now from here, we can just find out what is V2, which is the speed here. And then it's fine. I'm not going to apply this because you need additional information for you to find out what is going to happen here. For instance, you can find out how long it took from when they applied the brakes to them stopping. You can find out using these two equations. Once you know this, you can find out. But let's just do it. Okay. All right. I know everything here, here, and here. But then the only thing that I don't know is A1. I don't know A1. So I need to find A1 first. So I am going to use interval A and B to find A1. Why? Because between A and B, I know everything. I know the initial speed is 0. I know the final speed is 14, right? And I know the time is 18 seconds. So I can use the equation that says V1 is equals to V0 plus A1 delta T1, right? I call it delta T1. All right. So what is this one? This one is 14. This is 0. I don't know this one. This is 18. All right. This is 18. So I'm not going to explain a lot of things. So here is just going to be 14 over 18, basically 0 point something, 0.78. So the acceleration A1 is going to be 0.78 meters per second squared. All right, so that is what the acceleration is going to be, and it's going to be positive. Now that acceleration is maintained between B and C. So between B and C, now I can add the acceleration between B and C because it's maintained. Remember, he did not do anything between B and C. Even though he saw the robot when he was at B, he did not do anything. So he's still accelerating, accelerating. He only started applying brakes here. So that's when the change happens. So that is why the acceleration is going to be the same. It's going to be constant between A and B and C. So basically, we have the same acceleration between A and C. That's why I drew this line. So it's very important that you understand that. So this is going to be 0.8 meters per second squared. What is the velocity here? This is 14 and the velocity is V1 meters per second. And then what is the velocity here? V2 is the one that I don't know. Now the question is, do I know the time from B to C? Yes, they told me that it took him 1 second, 1.5 seconds to react. So which means that it took him 1.5 seconds. So this is T2, 1.5 seconds to react. So the time to move from B to C is 1.5 seconds. All right. So I can find V2. I can say V2 is the final here. What is the initial? Is V1. V1 is the initial plus A1, because I'm still using that acceleration, delta T2. You must now use this time. You can't use T1 because T1 is between A and B. So T2, delta T2 is between B and C, which is 1.5 seconds. All right, so it's very important that you know that. So what is V2? I don't know what is V2. This is 14, this is 0.78, and then this is 1.5, and then you find out what is V2. So in this case, this is 14 plus 0.78 multiplied by 1.5 is 15.7. So which makes sense. You can see that the speed kept increasing, 0.2 actually. So the speed kept increasing from here to here. The speed kept increasing. So here we find that the speed is going to be 15.2 meters per second. So you can see the speed increased. Then it started applying brakes here. Let me say, for instance, then the question comes out. They come out with the question and say, how long did it take for them to actually? How long did it take to come to a stop? Meaning that how long did it take to move from C to D? Right? The question can ask you something like that, right? Because you don't know how long it took there. Again, if you just break the question down, you will have a question mark there. I've already taught you how to break questions down in the drawings and put question marks, how to see where the question marks are going to be. All right. Now, remember, guys, if you master this type of approach, you're not going to go wrong with equations of motion. The only thing that is going to happen is you can misinterpret the question, right? So that is the only dangerous thing that can happen, you misinterpreting the question. But otherwise, if you can put everything down, you already know what they are going to ask you, and everything else. All right. So this is true generally for the equations of motions. It's actually generally true for most of the questions, except now when you start doing physics using calculus, it's very difficult to do this. But when for motion, you can still do it even if you're using calculus. But I mean, when you start doing charge, and then they just give you a surface, and then they say find the charge and show that the charge is going to be given by this equation. But I'm not going to teach calculus here. I'm just teaching algebra. I'm going to teach calculus maybe sometime next year when I have time to actually start doing physics that actually has calculus in it. All right. Okay. So let us see. So what is going to happen here is so from here you have from point A to point C. Now you want to find out how long it will take to move from point C. So let me not do that. How long it will move from point C to point D. So you're moving from point C to point D. Now at point D, you have the final velocity is going to be 3 meters per second. This is velocity. What is the velocity here? You just found out. What is that velocity? It is 15.2 meters per second. What is the acceleration? The acceleration is a2, which is minus 3.2. That's a lot compared to the acceleration that we had. Okay, so we want to find out how long it will take to actually stop. So we want to find out what is going to be delta t3. Okay, so I have the final velocities, I have the acceleration, and then I have the time. So I can still use this equation that says v3 v2 plus a2. This is why it's important to label things like what is a what, because so that you don't get confused and you don't confuse the person who's marking your script. Now, you don't want to frustrate the person who's marking your script. If you frustrate the person who's marking your script, you may lose marks because they don't have patience. So they're going to be very strict with you and all of that. So please try and be as clear as possible so that the person who's marking your script, it doesn't get irritated. All right. Now, V3, we know is going to be 0. And then this one we know is going to be 15.2. Now here we are going to substitute the negative because it's negative, it's decelerating. They told us what is the deceleration is going to be negative. And then here it is going to be delta T3. Okay. And then from here, we can solve for T3. I'm hoping you can solve for that. And then this is just going to be, this one will go that side, become negative. Then the negative and the negative is going to cancel. Maybe should I do that? Hey, let me do that. You take this thing, this side, and then it becomes minus 15.2. Then the equal sign is left, and then you are left with whatever is here. Because when you take this side, the equal sign moves to here. And then this becomes minus 3.2 delta T3. So you're going to, the negatives are going to cancel. You're going to divide both sides by 3.2. Let's do it. I'm going to do, this is the last time I'm showing you how to solve these equations. From here on, I'm just going to skip steps. And then you guys should know what I did, right? Generally, I would have done it like this. So this is going to cancel. This negative is going to cancel that. So I'm left with 15.2 divided by 3.2, which is 4.75. So it's going to take 4.6 seconds for it to come to a stop. All right. So after applying the brake, it's going to take them 4.6 seconds before they come to a stop. So this is how you actually use acceleration and deceleration. All right. And now let us now look at a case whereby I may actually have to do simultaneous equations. All right. So I would look at two situations. So let me see. I don't want to do opposite directions. Let's just do a car that is overtaking another car. All right. So what is happening is that you have a car. All right. You have a car. So there's an observer. So the observer sees car A. There's car A. All right. There's car A. And they see car A. Car A is moving from rest. So V0A. So I'll put A to show that this is for car A. It's moving from rest. Then they start accelerating. And then they accelerate, and after some time, maybe they reach a velocity of, this is V1A, which is going to be that acceleration. They're gonna meet some velocity. Let's just say this accelerates to 22 meters per second. All right, and let's just say it took them the time of 8 seconds. That's let's just say 10 seconds. It took them 10 seconds to actually get there. That is very fast. All right. At the same time, and then the car then basically keeps accelerating. The car just keeps accelerating, going forward. All right. They just keep accelerating. They don't change acceleration. All right. So I don't know what the speed is going to be when they are here, but they keep accelerating. So once the car was here, right, when it was just starting to move, there was another car. Okay. Then there was this car, and then this is car B. And car B was moving at a constant velocity. So this is V0B. And the velocity that car B was moving with was 40 meters per second. All right. And then the question is, when will car A find car B, basically, or overtake car B? All right. Remember, car A is accelerating. Car B is moving at a constant speed, which means that after some time, car B is still moving at 40 meters per second. Then after some time, they don't change their speed. They are still moving at 40. V2B is still 40 meters per second. All right, now I'm going to break this question down so that it makes sense now for you guys. All right, so this is how I'm going to break it down for you, and then it can make sense. So you can think of this like this is the road, and then you have two lanes. There's the lanes. So car A is in that lane, car B is on the second lane. All right, so how is this thing going to happen? All right, so I'm going to erase, I'm going to use everything here, okay, so that you understand. Now car B is moving at, the most important thing is that car B is moving at a constant, it's moving at a constant speed. All right, so that's the most important thing that you need to actually understand with car B. Now remember three things here. There's car A, there's car B, there's the observer. Remember, the observer is the one that is describing what is happening. So the first question is, where is the observer? Now let's say that the observer is here. Okay, what does the observer see? The observer sees car A, so I'm gonna have everything with car A is going to be black. So car A is at the same X position. I mean, they are both in the same position. If you were to draw a line, they are in the same X position. They are both at X is equals to 0. I mean, if you were to put a Cartesian plane here, you can see that both this and this, they are in the same X is equals to 0 here. I mean, this is Y and then this is X. So they are both in the same position. So X is equals to 0 there. That's how you know that they are both in the same X direction or X position. Sorry, not direction. So this is for car A. So remember, everything with black is car A. Now, when the car A was there, what was the initial speed? The initial speed was V0A, 0 meters per second, constant at rest. Okay. What else did they see? They also saw car B. There's car B. So this is the green color. This is car B. So everything green is going to be car B. All right. But then car B is moving at a constant velocity. So the velocity of car B here is going to be 40 meters per second. Now, since this one is 0 and this one is 40, all right, so after 10 seconds, car A will be somewhere here, right? There's an observer says that car is somewhere here. And when they measure the velocity, let's call this position 1, but it's 1 for A. That position is going to be, they have 22 meters per second. Now, the time that they took to move from here to here, okay, is the time that they take to move from there to there. Let's call it T1. And they actually took 10 seconds, all right, to reach the speed of 22. But now, and then after some time, they are going to be at some point here, all right? So they are going to at some point here. What is the speed at that point? I don't know, all right? Now, what do I know though? I know that since the car is going to be accelerating from, if I call this position A, I call this position B, I call this position C. What I do know is that the car is going to be accelerating from position A to position C at a constant acceleration, and that acceleration I am going to call it A1. All right, so that's what I know. This is what is happening with car B, with car A, sorry. Now the question is, okay, fine, then what happens with car B? All right, so when car A is here, car B is there. So they're in the same position. But since car B is faster, where is car B after 10 seconds? Car B is going to be somewhere ahead of car A after 10 seconds. All right, so this will be the velocity of car B after 10 seconds. All right, it's still going to be the same. Remember, it's not changing, it's constant. All right, then because this car is accelerating, it is going to accelerate and then keep speeding up. At some point, car A is going to catch up to car B, because here after 10 seconds, so this is after 10 seconds, after 10 seconds car B is here, So this is delta t1. So after 10 seconds, car B is here. But then after some time, we don't know how long that time is. That is the time at point C. We know there's a point whereby if this car A keeps moving at a constant velocity, then if car B keeps moving at constant velocity, car number A is eventually going to catch up. Okay, so let's call that position where car A catches car B, let's call it position C. All right, now the time that it will take to do that, we don't know what's the time. All right, so this is just showing you what the positions are going to be. This is going to be the velocity. It hasn't changed, it's still 40 meters per second. All right, so this is what you actually have to understand about this situation. Now the question may be to be asking you, how long will it take car A to overtake car B? So typically the questions will be going something like this. Now these scenarios, I could ask these scenarios in different ways, but just for teaching purposes, I think this is the most simplest scenario I can think of. But there's so many things I could do. For instance, I just thought now, like if I wanted to ask you guys in an exam, like I could just do this and that and that, and I could do so many things to actually see if you understand this. All right. So I could ask a similar question in so many different ways. All right. The red guy is the observer. This is car B. This is car A. All right. So, all right. So what do we know? What do we know? Okay. If both of these cars were in the same position when we started describing motion, all right, which means that the time on the stopwatch the observer had, which is t0, was 0 seconds. Then when the stopwatch was t1, it was 10 seconds. All right, t1. Even here is t1. Remember, now there are only difference in distance. This one is further, but the time is the same. All right, so when this one is here, the time is 10 seconds. When this one is here, the time is 10 seconds. That's basically what I'm trying to say. Now, after some time, T2, I don't know when. That's what I want to find out, basically, to say when will they catch up? When will they catch up, basically? Okay, so this is, I don't know. I don't know when to catch up. That's what they are asking me. All right, so but what I do know is that since they both started at the same point, even though they are moving at different positions, both of these cars are going to take the same time to move from point A to point C. All right, it's going to take the same time. So if you start counting here, you start at 0. When they meet one another, both of them would have traveled at the same time. It's just that different things happen before they get to that point C. This one is further away from this car, but then this one starts to catch on. Maybe this one, when they are here, maybe because this one now is moving faster, is now somewhere here. Maybe this one is here. Maybe now this one is almost there. Then when they are here, then this one is actually caught up with this one. So you can say that what is happening, this one is moving faster, this one is not moving faster. In any case, it's just moving at a constant velocity. That is basically what is happening. But then the time that it will take from point A to C for car A is going to be the same as the time that it will take car B. All right, so let's just say the time it will take car B and the time that it will take car A are both going to be the same. All right, so delta TB, which is the time from here to here, is going to be the same as the time that it will take the car from here to here when they actually overtake one another. All right, now it is very easy for me to calculate, for instance, how I can get that time for car B. So for car B, since the velocity of B is constant, so it doesn't matter whether I use V0B, V1B, V2B, it's the same. So I'm just going to call the velocity of car B, I'm going to call it velocity B, right? It's going to be given by delta x from A to C, because they started here and they are over, and then it gets overtaken at this point, divided by the time from A to C. All right, let's just call it the time from A to C. All right, how long it will take for it to move from point A to point B, to point C, sorry. Okay, and I know this, I don't know this, I don't know this. All right, so this is one of the equations. And then let's look at car A. What's happening with car A? So this is just one of the equations. Now, another thing is, how long will it take? How long will it take car B to move from A to C, basically? All right. Now, this is the strange part, because car A is accelerating, so I have to use an equation with acceleration. So delta x AC, this is the most appropriate equation I can use. Why? Because I know what is V0A, and then I'm looking for time AC plus half the acceleration. I called it A1, so this car will be accelerating with acceleration A1. This one, A2, is going to be 0 because it's constant. You remember I told you that when it's constant velocity, you just don't have acceleration. So that is why I did not even bother using the equations of motion, because I mean, this is the most probable equation that I can use. I mean, it's the only equation I can use, honestly, right? Because it's moving at a constant speed. All right, now for this case, this one is going to be a c squared. So the time that it will take car A to move from A to C. All right, so this is for car A, this is for car B, this is for car A. So you need now to understand whenever I'm using this interchangeably. All right, now let me just rearrange this equation. Since I have delta xac, let me also rearrange this equation to have delta x, delta xac. So delta xac is going to be velocity at B, delta t ac. All right, so this is what I'm going to have. So this is going to be equation 1, and then this is going to be equation 2. Why am I saying equation 1 and equation 2? Because I don't know quite a lot. I don't know the distance, I don't know the time. So of course I will need another equation. Immediately you have two unknowns, one equation, you will need another equation to actually solve what you don't know here. Then here, I don't know the time, I don't know this, I also don't know A1. So this one is problematic. I don't know three things here. I don't know the time, don't know the acceleration, I don't know the distance. Okay, so equation 2 seems like it needs more work. All right, so let's do more work for equation 2. Can I find the acceleration for equation 2? And the answer is yes, because I was given additional information. I was told that it's going to take 10 seconds for it to move from 0 to 22, which is going to help me find the acceleration. And that acceleration is going to be the same throughout. So I'm going to use that information to find the acceleration. So what I'm going to do is, okay, seems like it's behaving. So I'm going to say the velocity for car A, right, at this position 1, okay, you can't see it's out of your screen, at 10 seconds is going to be the initial velocity of car A plus A1, I don't know, delta T, I called it delta T1. All right, so which means that I am just using this interval here. So I'm saying I'm just focusing on this interval here. That can behave? No, it won't behave. All right, so I'm just just focusing on this interval from here to basically here, AB, right? That's what I'm focusing on. I'm focusing from A to B here. All right, and then I just want to find out the acceleration using the information that I have from there to there. All right, so that's what I have. And then this is basically going to work. All right, so make sure that you're not getting lost. I know that this one you can get lost easily. All right. So I have this one, v1a, v0 that, and then I can just substitute. I know that this is 22. I know that this is 0. I don't know a1. I know that this is 10. So I can solve for a1. 22 over 10 is going to be 2.2 meters per second squared. All right. This is what a1 is going to be. All right, now I know A1. So now I know A1. I don't know delta T. I don't know delta AX. But that's fine. At least since I know A1, now I can do something. So what can I do? Well, I can say equation 1 is the same as equation 2. So I equate the two. On the left-hand side, I have delta AC. On the left-hand side of equation 2, I have delta AC. So they are equal, right? So equation 1, the left hand side is delta x AC, and equation 2, the left hand side is also delta x AC. So I can just substitute. So what is delta x AC for equation 1? It is VP delta T AC. What is that for equation 2? It is V0A, which is 0 anyway, delta T. So it's going to work out nicely because it's going to cancel actually. That is very nice. And then delta TAC plus half A1 delta TAC squared. So let's substitute the values. This is going to be 40. I don't know this, so I'm just going to call it delta T from now. I'm lazy to write AC now. This one is going to be 0 delta T plus half A1 delta T squared. So what I'm left with 40 delta T is equals to half A1 delta T squared. And then from here, I can actually I can cancel. So one of the T is going to cancel this. So I'm left with 40. And then I cross multiply this one, this side. So it's going to be multiplied by 2. I have A1 delta T, right? So I divided both sides by delta T this side, delta T this side. All right. Then I cross multiplied by this. All right. Maybe let me just show you what I did so that in case some of you are still confused, this is what I did. I said this is half A1 delta T squared. So I divided both sides with delta T. I divided this side with delta T. So this is going to cancel. And then one of this is going to cancel that. So I'm left with half of that. So I'm left with 40 is equals to half A1 delta T. And then I cross multiply. So this is going to multiply here. And then this is going to be multiplied here basically. All right. So 1 times 1 is going to, remember there's 1 here over 1. We don't write it, but there's 1, there's always 1. So 1 times 1 is 1, and we don't write it. 40, then it's going to be 40 times 2 here. So that's how I got this step here. All right. Now I did find this is 2.2, so this is 80, 2.2 delta T, and therefore delta T is going to be equals to 80 divided by 2.2, and then I'll find that this is going to be 30 something. All right. So 80 divided by 2.2, 36.4. So it's going to take 36.4 seconds in order for this car to catch up. All right. So from the time when the observer saw that car to when actually the car catches up with that one, it's going to take 36.4 seconds. That's basically what it means. All right. So this is how you use the equations of motion. Now, this is the simplest example that I could think of, so that I show you how to see when you're going to use equations of motion. Now, of course, you have to find more problems, and you can go to different textbooks. And then I'm not sure if metric is going to be heavy on this type of things. I don't think so. You should just expect this at university. Just expect this, and we don't even think it's difficult for you, because it shouldn't be difficult for you. All right. So, and it won't be this simple as well. When you are asked this question at university, it won't be this simple. It will be more complex cases. I can think of a number of cases that I can ask, for instance, my students as well. All right, so this is fine. This is good. And then for equations of motion, I think this is fine. This is good. And then we can now move to another section that actually gives students problems, and that section is actually graphs. All right, so we're just going to move on those one and then we'll find out what to do.